Hello guys, good afternoon, happy Monday. Can you guys hear me? It's the day before Physics Paper 1. How are you all feeling? You can see and hear me okay? Just let me know in the chat. Hello, I'm getting some hellos now. Do we get the workbook by ourselves or are they going through it? So the purpose of today is we're going to go through the workbook that we sent you. So I'll go through each topic 1 to 4 today in Physics Paper 1. We'll go through a few notes and then we will attempt some of the questions in the workbook, get through as much as we can. So as you guys know, we've had biology, we've had chemistry already. Hopefully you guys have found it useful and the exams went well for you. We're now on to physics today. Yeah, so Physics Paper 1 with the exam being tomorrow. And this is the last of our 3 classes, guys. So from then, we're going to be looking at our Paper 2s. And then that will start from Sunday the 7th. So this Sunday, where Neen will do biology Paper 2, and then followed by that Thursday the 11th of June for chemistry Paper 2, and then back with myself for physics Paper 2 on Sunday the 14th of June. So if you found these useful, please do join us for those sessions as well. So yeah, look forward to seeing you there. And thank you guys for turning up today and look forward to going through everything in the workbook today. So where's the workbook? We sent it to you via email when you signed up. So you should be able to have access to it. If you go there, you can open the workbook from there. And I'm going to be going through exactly what we need to cover from there in today's session. Hi, King. Thank you. Good to see you. Is this AQA? Yes, it's mostly AQA, but obviously there's a lot of transferables between this and the other boards as well. I'd say 70 to 80% crossover, especially in combined science. It's a lot the same. It's just the topics sometimes in a different order. So content-wise, very, very similar. Is this good for foundation? Yes, it's for both foundation and higher tier. So yes, very useful for all of you. We're covering questions that are on both as well. So it should be useful to you for sure. How long? So basically with the session, we're going to be going for about an hour per topic, roughly, yeah, there or thereabouts. So where I do about maybe 15 to 20 minutes of notes, and then I'm going to be trying some questions with you guys. So please do get involved with me as I'm trying the questions. Drop your answers in the chat, and I will make sure I'm paying attention as much as I can, as much as you guys are messaging. And then I'll do that for topic 1, give you about 10-minute break or so in between each of those topics as well. Yeah, from 2 to 3 to 4. So today we're not covering triple, Molly. We have done this in our bootcamp. So if you want to cover a bit of triple content, make sure to check out our bootcamp videos, which you have access to the links for. This is for everyone to give a common ground for everybody. So it's going to be foundation and higher tier combined science. You need the workbook. You signed up already. It should be in your email. Please do take a look. It should be in your email, and you should be where you got confirmation of you attending the class, where you got the link from. You should be able to get access to it from there. It's good for IGCSE. Yes, it is. It's good for all the boards really, because there is a high level of a crossover. Yeah, it may not be 100% the same, but there's a lot of the comments where they are the same. Okay. Hey, I'm good, thank you. I'm good. Looking forward to getting into this. So yeah, hopefully it will be helpful for you guys getting into your exams. Is there a mark scheme for the workbook? Yes, there is. Okay, so whatever I don't get through today, we will send a mark scheme right after this session. Okay, so at the end of the session, you should get a mark scheme sent to you as well. So for any questions that I don't cover, you should get access to those, and you should be able to check those as well. Where's the other guy? K-Star. Neen covers biology and chemistry. I am the other guy. My name's Nav, and I cover physics at FRL. So for the physics one, so for now paper 1, and if you join for paper 2, I will be covering for physics. Where can I get the workbook? It should be in your emails, okay? So please do take a look for the confirmation where you got it. That's where you'll get the workbook from. Okay. For anything else, like I've got here on the screen, please do email us at help@flashrevisionlab.com. Yeah, if there's anything else you need, our team will do our best to answer for you. Okay, so hopefully you can see me and hear me fine. So I'm going to make a start now, and we're going to get into our paper 1. Okay, so having a look here, some of the topics I wanted to cover, as we have done in the previous sessions, we've been looking at particular topics that seem to come up more frequently in papers that we've seen in the past, given our research, what's been the more common topics in both foundation and higher, and then also some of the key things I want to cover, so like required practicals, which I want to cover for all paper 1 and paper 2. So today I'll cover all the required practicals we need to know as well. And I'm pretty sure when I made this workbook, I've put questions in there as well. So if we don't get to it, you can definitely try them also. Okay, so you can see here the topics I picked: energy changes in systems and energy transfers in systems, slightly different topics, okay? Energy changes in systems, as the name suggests, the energy changes. So like we need to know the energy sources and what their different changes are when we transfer between the different types. Energy transfers is more to do with the equation side of things. So what the equation for energy is and linking it to power and how we use that in questions. I then also got a bit on power itself as well in a bit more detail. And then something on efficiency as well. So what the equation for efficiency is and how we use it in questions. Okay, so for people, first of all, can someone tell me what is the law of conservation of energy? Does anyone know what that is? Hopefully you do a day before your exam. If not, it's a very important point to note, the law of conservation of energy. I'm just going to write that here. If anyone can tell me, I will put it shortly. When something is conserved, what does that mean? Yes, people are dropping it in the chat. Energy can't be created, only conserved. So I'd say it can't be created or destroyed. It can only be transferred. Yeah, so energy cannot be created or destroyed. It can only be transferred. Now, can anyone tell me what the unit for energy is? How do we measure energy? How do we measure energy? Where's the workbook at? A few people have asked a question. The workbook is in your email. When you got confirmation when you signed up to join this Cram class, it will be in your email. So if you're having any issues, remember, email us at help@flashrevisionlab.com. One of our team will get it sent to you, but it should be in your emails. Please do check. Joules, excellent. Loads of people dropping it in the chat. Energy is measured in joules. Yeah, correct. So we're going to see that a lot in this in paper 1 because there's a lot around energy in several of the topics. Yeah, not just this topic 1 that we're looking at, but we'll see it later on as well. Okay. This is an AQA triple, Mariam. This is AQA combined science. If you want triple content, please do look at our bootcamp videos where we go through the whole syllabus and we've covered triple there as well. Okay, so energy, as we've said, is measured in joules. So anything else I want to mention? Key things such as, let's say, what is the equation for efficiency? Can anyone tell me? When you're looking at the efficiency of an energy transfer, what are we looking at in terms of the equation? I'll give you a clue. It's a fraction. Can I make the pen thicker? No problem. Yes, I definitely will. Sorry about that. I will cross out this last one and rewrite it. Let me know if this is better. I can go one thicker if you need to. Efficiency, yeah, hopefully that's a bit better. Is that okay? What does efficiency equal? So someone's put useful power output over energy transferred. You've used two different things there, power and energy. Okay. You should stick to one. You either mention power or you mention energy. And the way we put it is it's useful, and I'm going to refer to energy here, useful energy output over the total energy input. Okay, so what energy is put into the system. So here you can replace energy with power and you have the same equation. Okay, so which one should I watch for triple? So the triple only parts, it's in the bootcamp. Okay, this is going to cover everything else. So this is the large bulk of the content that you're going to see in triple is also here, right? It's in combined. For this very specific triple science bits, they will be in the bootcamp video. Okay, this is for foundation and higher tier, by the way. I know a couple of people have asked as well. So yeah, the equation for efficiency, again, with equations in physics, you will get them in your formula sheet, but it's all about applying them. And that's what we're going to be practicing today. Okay. So that's one. Now, the other equations that we see, exactly, we don't need to memorize the equations. Exactly that. Yeah, that's what I'm just getting to. It's just knowing how to apply them. Yeah, so it's knowing where they are. Okay. So we don't need to know the equations, but we do need to know the different types. Okay, so the key ones that we get asked, which are related to equations, are these three: GPE, KE, and EPE. Yeah, in other words, you would see it as EP, EK, or EE. Can anyone tell me what these three are? What is EP, first of all? Refraction practical for Edexcel, that is in paper 2 for us here. So I'm going to be covering that in our next session. So join us in our next session for that one. And if you need to look at notes on it, remember we've got bootcamp videos out there as well on our page. And if you joined our bootcamps, you'll see those. People have said MGH. Gravitational potential. Gravitational potential is what I'm after. Exactly. Yeah, so that is what GPE or EP is. And that is energy dependent on the position, right, or height of an object. So energy due to height / position. Yeah, that's what determines the potential energy. The higher the object is, the more gravitational potential it has. What about for kinetic energy? KE people have said is EK is kinetic energy, correct? What is that energy dependent on, guys? Can anyone tell me? What does it depend on? How do you have more kinetic energy? What does the object do? It's all about movement, exactly. Yeah, the more movement it has, the more speed it's moving with, the greater kinetic energy it's going to have. So energy due to movement. And then the last one, EE, I saw people mention it earlier. EPE is elastic potential energy, right? What is the energy? There we go. People have mentioned it. Excellent. What is that dependent on, guys? Can anyone tell me what does elastic potential energy depend on? The clue there is like it's elastic, so like an elastic band. What do you do with an elastic band? Spring, someone says stretch. Yeah, people are saying stretch or compress. Yeah, so energy stored when you stretch or compress an object. So energy stored when stretching or compressing is the word I'll use. Obviously, squashing is what I mean by that, but the best term to use for it is compressing. Yeah, so when you stretch or compress an object, that's when you have elastic potential energy. Okay, and what happens is that you'll get energy transfers between these that they discuss in questions. And we're going to see some that I've put in here as well that lead to that comparison. Okay, that's some of the stuff I wanted to cover. Another bit I want to get into before we get into some questions is energy resources. Okay, so there is sometimes a mention of this as well. What is can anyone? I want to see just a mention in the chat. What energy resources are renewable resources that move us into a more sustainable world? So this is what we look at, right? Electricity generation. We don't want to. The main problem that we're seeing is fossil fuels, right? That is running out, and we need to find an alternative way to do it. Excellent, guys. I'm seeing solar, hydroelectric, geothermal, tidal, waves, wind. Anything else there? Tidal, water. Yeah, hydroelectric. Someone's mentioned that already. Yeah, great. Loads of good shouts there. Yeah, everyone's mentioning the right things. Biofuel, someone mentioned as well. Excellent shouts. Yeah. So the aim of that is a renewable source. What does it mean if it's a renewable energy source, guys? Can anyone tell me? Nuclear is not renewable, correct. Nuclear, someone mentioned that is non-renewable. Never run out, exactly. As well, yeah. So never runs out is what I'm going to put here. And non-renewable, as it suggests, is the opposite. It will run out. Yeah, so that's the main plus side to a renewable energy resource. So all of those types you mentioned, geothermal, solar, wind, etc., that can all be can be replaced, can be replenished. It just never runs out. It can always be used forever. That's the key point. It never runs out. Okay. So what we compare is that's a big advantage of using that. But the disadvantages you need to consider can vary for different examples of those energy resources. Key things being you need to consider cost, whether it's more expensive or not, how much energy output it gives, because fossil fuels give us a lot of energy. As we can see, it provides the whole country with electricity in several countries. But these energy resources may be less so, like things like wind power, solar power. We know we don't get the sun, especially in this country, not that much. I know we did last week, but it's going down now. Yeah, and that doesn't give us as much output. So that's the thing to consider. Okay, so I'll say points to consider when comparing renewable energy resources or energy sources. And one thing I mentioned is energy output. The second one I will say is the cost of it, so cost to install. So to fit and set up that particular piece of equipment for that energy resource, is it expensive? Is it not? Yeah, the energy output. And then someone else has mentioned reliability. Exactly. Yeah, so that kind of goes hand in hand a little bit with the energy output, but it's a good point to mention. Yeah, mentioning whether it's reliable or not. Location, someone's mentioned, an excellent shout again. Yeah, excellent. That is also another option that you can mention. So I'll mention there that its location is also important. Yeah, these are certain factors that you need to think about. So cost to install. Next to that, I'm also going to put cost to run. Yeah, once it's set up, does it cost a lot to maintain and run it? Yeah. And then the last thing I want to mention is environmental impacts. This is a big one. We know what is the big impact of fossil fuels, guys. There you go, environmental friendly habitats. Nice. Sub-X has mentioned that. What's energy output? So energy output means, so say for fossil fuels, I burn fossil fuels. How much energy does that produce for me? Yeah, to give electricity to the our country, yeah, for example, into the national grid. That's the output. How much energy is it producing from that resource? Yeah, so whether we're burning fossil fuels, comparing to using a wind turbine to spin and generate electricity, how much energy is that generating? That output of that. So, yeah, all excellent shouts. But the big one here, like I want to mention, is environmental impact. Okay, so that can be things such as fossil fuels cause global warming, but things like nuclear resources cause radioactive waste. Yeah, and like people have said, affecting marine life, quarrying affecting land animals, things like that. Those are the things we want to be careful of. Okay, so that is in the energy resources topic. So it does come up as well. Yeah, so that's why I'm mentioning it. It is something that can come up. Okay, cool. So I've had a look at a bit of the content here. Now I'm going to go through some of these questions. Okay, so I've got a variety of different things here. Actually, last thing before I do, very, very important bit that I want to cover is the first required practical that we see is in topic 1. And the very first required practical is the one for specific heat capacity. So specific heat capacity, the equation leads you to the important steps here for this. Okay, so specific heat capacity, we know the equation, again, given in your formula sheet, is mass times specific heat capacity times change in temperature. Okay, so you think about that equation and then you go, what do I need to be able to solve that? That's the last step in this experiment. So you need to find all of the other pieces of information to help you figure that out. So if C is what we're trying to find, that's a specific heat capacity, we need to know the energy transferred, the mass of the substance we're investigating, and the change in temperature of that substance. Okay, so when you talk about a required practical all the time, when they talk about how you describe your experiment, you talk about the apparatus, the method, and how you get your results. If you're getting 6 marks and you're getting 2 to 3 points in each, you're more than fine to get your 6 marks there. Okay, so for this one, what apparatus are we going to need? So I'm going to say SHC experiment here. Shout out any piece of apparatus people know. Can anyone tell me? Mnemonics, when I get to them, I will bring them up. No problem. Absolutely, I will. So, immersion heater, excellent. So I'm going to say apparatus, or in other words, equipment. Immersion heater is one, or some sort of heater, correct? The thermometer, very important because we're measuring temperature, right? That's what you need to think of. So how are we going to measure the energy and how are we going to measure the mass? Those are the other 2 important bits. Someone's mentioned it. DJ, I think it is, a joule meter. Yeah, a joule meter is what measures energy. And then a mass balance. There we go. D just mentioned it again. Nice. Yeah, sorry, I'm sure other people have. It's just coming to my eye as to who said it. A mass balance. Yeah, so you measure the mass using a mass balance. You use a thermometer to measure the temperature before and after heating. And then you get the energy change from the joule meter. So that covers, like I said, mass from the balance. Thermometer gives the temperature. Joule meter gives the energy. You've got all those things. And the last thing you mentioned is use the equation delta E equals mc delta theta to give you the specific heat capacity. And those are your steps. Yeah. So you wouldn't say kettle to boil the water. So this is where we've mentioned the immersion heater here. You can either mention an immersion heater or an electric heater. Yeah, one or the other to heat up the substance, whatever it is, whether it's oil, whether it's water, whether it's a metal block, yeah, whatever it is. So this is for a solid substance. So immersion heater is usually the one they refer to in this required practical. So an immersion heater, Janet, is essentially, let's say we had our material and it was a metal block like this. To immerse something in something is to put it inside of it. Yeah, so when you immerse something, it becomes surrounded by it, essentially. So the immersion heater would be like this, and it has a gap in there that you drop the metal into. Yeah, so let's say this is our metal, and this is the immersion heater. And then that will be connected to the circuit, and it warms up, and it surrounds the block and heats it up. So that's what an immersion heater is. Yeah. A thermistor is a heat-dependent resistor. Yes, that's correct. It's lagging. Okay, bear with me if it's lagging. If you can hear me, that's the most important thing. I'm going to talk through everything, aren't I? So make sure you're listening to it. Hopefully the connection will kind of come back to you. And then, yeah, sorry if you can't see. Sorry if you can't see. Give it a minute. If you want me to scroll up, I'll scroll up a little bit. You can see what I've written earlier. Remember, you can go back in this video, okay? So you can have a look at where I've written this in the first place. So if it's lagging, bear with me. Probably a bit busier now as it's about coming near to 6 o'clock. Victoria, this started at 5:30. I'm just about to get into the first section of questions, and we're going to finish at about 9:30. So I'm going to be going through topic by topic. We're only on topic 1. You haven't missed too much. We're about to get into the questions. Okay, cool. Nothing's lagging. Okay, people are having mixed. It could be my connection. It could be yours. But there we go. That's a brief run through of topic 1. I'm going to go through some questions, and let's see how we get on with them. Okay, so any multiple choice ones, just mention in the answers A, B, C, or D, or 1, 2, 3, or 4 if you like. So you can see if you get these right before I mention the answers. But first one here. Figure 2 shows an outdoor swimming pool. The water in the swimming pool comes from the sea. The water in the pool is heated using a geothermal energy resource. Which of the following describes a geothermal energy resource? Is it non-renewable with high carbon emissions, non-renewable with low running costs, renewable that uses hot rocks underground, or a renewable energy resource that uses the tides? C. A lot of people have said C. Good to see everyone's on the ball. It is C. It's a renewable energy resource that uses hot rocks underground. Okay. The way you get the idea of that is I split this word geothermal into 2 bits. Geo for geography, and in geography we learned all about the land and stuff. So that's like ground, to do with the ground, and then thermal, as the name suggests, is to do with warmth and heat. So it's like ground heat. So here is rocks from underground, rocks from the ground that heat up the source, whatever like the water that's usually running through there. Okay, so that is the type that is here. Okay, excellent. So that's the first one. The second one here, 15 kilograms of seawater is heated before it is added to the pool. The specific heat capacity of the water is 3,800 joules per kilogram degrees Celsius. Calculate the change in thermal energy of 15 kilograms of seawater when its temperature is increased by 9 degrees. And they've given you the equation here. Like I said, you'll get it in your formula sheet. Change in thermal energy equals mass times specific heat capacity times temperature change. So we've seen this before, as I wrote in the notes. I'm just putting it all in letter form as I showed it above. Delta E equals MC delta theta. Okay. And as you can see, as I went through the question, I underlined all the key things there. Okay. Either numbers that I need to use or the point that they want me to find. They said calculate the thermal energy. So I've said that's what I'm trying to find. Then everything else they've given, specific heat capacity is here. That's C. 15 kilograms is a mass. So that's M. And then change in temperature, increase of 9 degrees. That's where our delta theta comes from. Okay. So we're given this, we're given this, and we're given this, and they want us to find the change in energy. I can see people dropping the answer in the chat. You guys have done a good job. That is correct. I'm just going to quickly write down the working out then, and that is the mass of 15 times the specific heat capacity of 3,800 multiplied by the change in temperature, the rise of 9 degrees, and that gives you a value, as people have said, 513,000 joules. Very, very good. And in this case, you can see they've given you the unit, which is why it's 3 marks. Sometimes in questions, they'll say state the unit, which is why I asked you at the beginning, what is the unit for energy in joules? And it's joules, correct. Light work, Sammy, good to hear that. It's good that it's light work. I will zoom in a little bit more. Thanks for giving that shout out. Just let me know if you can't see it. I'm happy to zoom in as needed. Okay, excellent. If it's lagging a lot for you, and it's not for others, I'm inclined to think that it's not my connection. Hopefully, maybe it's your connection. Just give it a refresh, maybe, and then obviously you can come back and pick it up where we are, or you can just stay a little bit behind, so it gives it time to build up the connection for you. Okay. Apologies for the ads, guys. Just the way YouTube is. Sorry about that, but just jump straight back in, and hopefully you don't miss too much. Okay, so the energy transferred from 1 meter squared of the surface of the pool to the air is 80 joules each second. Okay, The surface area of the pool is 120 meters squared. Calculate the energy transferred from the whole surface of the pool to the air each second. Okay, so it's still saying each second. So they've given us for 1 meter squared, it's 80 joules that's transferred each second. And now they're saying the pool is 120 meters squared. So people have mentioned it in the chat. They've given a number. If they've given us the energy for 1 meter squared, they want us to find it for 120. We just need to times the energy by 120. So our calculation here is 80 joules times 120 to cover the whole area, which is in fact 9,600 joules, which people have mentioned in chat. Well done to those of you that got it. Very good. Good. Can you use this for OCR 21st? Yes, you can. Again, all the boards, there is so much crossover. It's like at least 70% of it's going to be the same. It's just topics might be in a different order number for you. Like topic 1 in AQA may not be topic 1 in Excel and OCR, basically. But loads of it is similar. There is a mixture of foundation and higher tier questions. Okay, so I've gone for a bit of... so this one is, I believe, a foundation one. But it's doing both. Yeah, so this is actually, I think this may have come up in both actually, just as a different question number, essentially. So that's what I've tried to pick, something that's common to all of you. Okay. Cool. Which of the following units is the same as 1 joule per second? Who can tell me? Someone said A. Do 5 markers. We will be coming on to 5 and 6 markers. Don't worry about that. We definitely will. Okay. So stay tuned. We will be going through those shortly. A mixture of A and C, okay? But the large majority is C, and those of you in the majority will be correct, okay? 1 joule per second is 1 watt, yeah, joule per second. If we break that down, joules is the unit for energy, right? And then time, seconds is the measure for time. So if you went to your formula sheet, you take those and go, okay, what equation has energy over time or can rearrange to give energy over time? You'd see that it's power, and the unit for power is watts. So very good. Okay, the pool is above sea level. 5 kilograms of water is pumped from sea level. Lots of people have got the answer, or someone's got the answer already. Let's see if they're the right or not. Some people are going to be putting their answers now, so I'll see what you have to say. The pool is above sea level. 5 kilograms of water is pumped from sea level into the pool. The water gains 196 joules of gravitational potential energy. Given that gravitational field strength is 9.8 newtons per kilogram, calculate the height of the pool and use the equation height equals GPE over mass times gravitational field strength. So they've even rearranged the equation for you here. Okay, so we just need to look at what information they've given us. They want gravitational potential energy, which is 196, and then over mass, which is our 5 kilograms, times the gravitational field strength, which is 9.8. So they've given everything. We just need to substitute in. So H, or height, equals 9.8 over the mass of 5.0 kilograms times 196. Oh, sorry. I've got it the wrong way around. Apologies. It says gravitational potential energy on top, doesn't it? And this is where always check. Yeah, so I spotted that it's the other way around. It's energy on top and gravitational field strength on the bottom. So instead of 196 here, it's going to be 5 times 9.8. Okay. And if you put that in your calculator, you're going to get 196 divided by 49. And as people have mentioned, that is 4 meters. And there's your answer, 4 meters. Excellent. Very good. You shouldn't get a decimal. So if you ever got 4.13, not quite right, but unless that's some sort of symbol. But 4 meters is the answer there. Very good. Okay. In the water in swimming pools is heated by burning fossil fuels. Explain one environmental disadvantage of burning the fossil fuels. Now, be careful here. It says explain one environmental disadvantage, but it's 2 marks. Yeah. So what they're saying is for 2 marks, you need to essentially state what the disadvantage is and how that happens, basically. So can anyone say what they are? There's several options you could come up with here. Some people are putting it in exactly. So some people say greenhouse gases. You could say that, but I would say more specifically, as some people have said, CO2 or carbon dioxide. Okay, so carbon dioxide, and someone has mentioned it in capitals. Some other people have as well, about what it leads to. Yeah, what does that cause? That causes global warming. Okay, so for 2 marks, I'm going to put it as bullet points. 1 mark is simply for stating which gas causes a concern, in this case, carbon dioxide. And you can say this contributes to global warming. Or I'll say carbon dioxide is released. Yeah, just so we know from burning fossil fuels, carbon dioxide is released. And then for the 2nd mark, this contributes to global warming. Excellent. Yeah, so a lot of people A lot of people have put that, and also other people are right. Someone said sulfur dioxide, which causes acid rain. That's another option, and saying those 2 points exactly gives you 2 marks. So one for the gas, one for the what it causes. Yeah. And then someone else has said it. I was just about to say soot is another option, which is global dimming, right? It makes the world darker. So global dimming is another one. Correct. Excellent, everyone. Yeah. So all 3 of those are viable options. Brilliant. Okay. On to ask for a 6 marker. Here we are, a 6 marker. Okay. And if we take a look, you can see the equipment there. It's something that we've looked at just before we got into this about specific heat capacity. Okay. A student made measurements to determine the specific heat capacity of vegetable oil. Figure 2 shows the equipment used. So you see several of the things that we mentioned, right? Joule meter, top pan balance or mass balance, thermometer. Then what I've got here is a beaker and an electric heater instead of an immersion heater that we mentioned. Okay, you did this in school, excellent. So you're going to be very easily finding this 6 marks very quickly. But let's see if you can get them here or reproduce them here. Describe how the student could use the equipment shown in figure 2 to determine the specific heat capacity of vegetable oil for 6 marks. Okay, so it's method. We're talking through all the steps here. Okay, so place vegetable oil and measure the mass. What are you placing the vegetable oil in? You have no clue, don't worry. This is exactly why we're doing it, okay? And this is what you're going to have for you. Is momentum a topic in this paper? No, that's a paper 2 topic for AQA, okay? So we'll be covering that in the paper 2 session on the 14th. In the beaker, exactly. So it sounds stupid in a way, like you're like, well, where are you going to put the oil? But just make it obvious to the examiner, okay? So we're going to say, for the first mark, pour vegetable oil into the beaker. So we've highlighted the first piece of apparatus we've used there. And then we're going to place the beaker on what? Because we want to get the mass. What are we going to place it on? Place the beaker on what piece of equipment? Top pan balance. Excellent. Yeah, people dropping it in on the top pan balance. And record the mass of the oil. Okay, so pour the vegetable on the beaker. Put the beaker on the top pan balance and measure its mass. Then, having a look here, remember it's specific heat capacity. So you could say it's a fixed amount of oil. You just need to some way of saying that you're measuring the mass. Okay, that's what you need to mention. Because someone could pour a different amount. As long as you measure the mass when you're doing it, that's the important thing. Okay. What can you explain the required practical? Is exactly what we're doing right now, Amina. So just follow these steps. This is what we're talking about. This is what the required practical is. It's exactly this. Okay. So we get our substance and we record its mass. In this case, it's a liquid. So we put it in a beaker and we're measuring the mass of that liquid on the top pan balance. Okay. Then exactly, people are starting to mention it. Thermometer to record the initial temperature. Okay. Because the aim is we're trying to find the specific heat capacity. Okay. Specific heat capacity, if you go to your formula sheet, the equation for that is delta E equals mc delta theta, where specific heat capacity is this, the C in the equation. So we need to use our method to calculate or work out the other pieces of information, these 3, okay? So M being mass, that's the first thing we've done. Now we're looking at delta theta, theta being temperature. So temperature is measured using our thermometer here, okay? So now I'm going to say, as has been mentioned in the chat, I'll change back to my color here. Record the initial temperature of oil using the thermometer. Yeah, so always stating what piece of equipment you're using. Again, I know it sounds obvious, but you just want to treat the examiner as if they don't know anything, yeah, and you're explaining it to them for the first time. So record the initial temp of oil using the thermometer. Okay. Do you add an insulating layer? If it talks about in more detail about what you can do to make the experiment more accurate, yes, you can mention it. It's not in the apparatus here, so you don't need to mention it in describing the experiment because it's not in the apparatus. So, but it's a really good question. Okay. Which experiment is this? This is the experiment for specific heat capacity. Yes, the required practical for specific heat capacity. Okay. Cool. So the next thing is we've got the initial temperature of the oil. Now, to find a change in temperature, we need to actually change the temperature itself, right? So we need to start heating up the oil. The thing that's going to heat up the oil is the electric heater. So we say switch on the electric heater. And then what we're going to do is measure the final temperature of the thermometer, right? At the end, once you've finished heating. Yeah? So I'll say switch on the electric heater and heat the oil. And now you can mention a specific time frame if you like. It can be 5 minutes or 10 minutes, something like that. Okay? For 5 minutes, let's say. Then we want to record the final temperature on the thermometer, of the oil once you finished heating. So now the next step is record the final temperature of the oil. Again, I'm being obvious using the thermometer. And then we want to also, this is where it's connected to the joule meter, right? Because here we have an electric heater, but to record the energy that is produced from the electric heater, it's connected to this. And you're just simply reading what's on the dial of the joule meter. Okay, so you'll say record the energy transferred using the joule meter. So what have we got from our equation so far? We recorded the mass. We recorded the change in temperature, right? Initial temperature before we started heating. And then we said after heating for 5 minutes, record the final temperature. We then also said record the reading from the joule meter. So that's our change in energy. Okay. So we've got all of those things. Now we can calculate that change in temperature, right? We've mentioned we've got an initial and final temperature. We haven't calculated its change. Okay. So the next thing here is I'm going to say calculate change in temp by doing the final temperature minus the initial temperature. For example, when it starts and we haven't started heating, the liquid is likely, in this case, the oil is likely to be at room temperature, like 20 degrees. So once we heated it for 5 minutes, it might have risen to like 50 degrees. So we do the final minus the initial, in this case, 50 minus 20 to give us 30. Yeah, so this is what we're stating. We say calculate the temperature change, and that's what we do there. So we have everything in our equation now, right? Delta theta, mass, and delta change in energy. So the last thing to state is use the equation to write to calculate the specific heat capacity. So I'm going to say calculate C using the equation delta E equals mc delta theta. And there you have it. We've calculated our specific heat capacity. That's what it's asked us, right? Use this experiment to determine the specific heat capacity. And that's what we've done. So do you have, can you write it in bullet points? I think someone asked. Yes, you can. And then even if they mention to write it in like with where they're evaluating your English skills, I think usually the question sometimes says, as long as if you're writing in bullet points, but you're in sentence form, you're fine. Yeah, so it's a good way even to show the examiner how many points you've covered by putting it point by point. So here you can see I've got more than that, I think. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so I've got 8 points for a 6 marker. I've definitely broken it down as much as I can to give us the 6 marks. You can mention about repeating the experiment. It's a good point to make. You can mention it, not necessarily a must in this case, because it just says how you determine the specific heat capacity. If it's talking about making sure your results are accurate, if it mentions points about how do you make it reliable and make your results accurate, then I'd mention things like the insulating layer and repeating your experiments and calculating an average and all of that. Okay. Apologies if I'm missing you. I see someone said they're ignored. Please drop your message. I just missed it. Apologies. So just drop your message again and I will catch it. Sorry about that. Is there any errors? In this case, no, but obviously, again, that's the thing about when you're trying to make sure the experiment is done accurately or reliably. Okay. How many other ways could this question come up? Not in many different ways. They may not show you the apparatus, maybe. Yeah, the one thing is they may not show you what apparatus is involved. You will need to remember these things, the joule meter, the mass balance, the thermometer, and then either using an immersion heater or an electric heater in this case. But in our required practical in the notes, if you look back, it's about sorry, I mind blank. It's about the immersion heater. That's what they mentioned in the notes. So if they don't give you the image, I would refer to using an immersion heater to heat the substance, especially if it's a solid. Okay. When you measure the oil, do you measure the mass of the beaker? So essentially, yes, you could, if you wanted to break it down, you could say measure the mass of the beaker, and then measure the mass of the oil in the beaker, and then subtract the two. You could mention that. Ultimately, they're just, as long as you mention that you're measuring the mass of the oil using the top pan balance, you'll get the marks in. Okay. Difference between random and systematic error, I'll come to that shortly. What is a joule meter used for? So if you think about the term joule, we talked about it earlier, energy is measured in joules. So a joule meter measures energy. Okay, it measures energy transfer. So a joule meter measures energy transfer. How do you use a joule meter? You just connect it to the circuit. Okay, so it's connected by a wire. So this circuit will be complete with the power supply, and then you turn on the electric heater, and the joule meter is going to record as soon as you turn the electric heater on. Where do you get the paper? You should have access to it when you signed up to this session. If you don't have it, send us an email at help@flashrevisionlab.com and we can send it to you. I'm scrolling back down, but guys, remember, this is a session that's on a video, so you can scroll back to look at the answer. So please do take a look back, and you can see what the points that I've mentioned are. For this one, I don't have a particular memory trick in mind, but it's something I definitely have to work on, I think. But I'm just trying to think what's the best way to do it, because you're thinking M, mass, then temperature, then energy, and then the specific heat capacity. So you could say, I've literally just come up with this now. Yeah. So if you don't like it, that's fine. But I'm going to say mates. So if you're thinking about the order of the experiment, it's mates, small a for and. Okay. So I'm going to say mass. So where this stands for mass and temperature, energy, and specific heat capacity. Yeah, so that's the order of it. So I'll say mates is maybe the way to remember it. Mass and temperature, then you find the energy, and then you find specific heat capacity with the equation. Yeah. So hopefully that's a useful one. I don't know. I've just come up with it off the top of my head. Maybe it's something we'll make a video out of. If anyone can think of anything else, always welcome to hear your suggestions. But just a freestyle mnemonic for people that had asked. Okay. Yeah, don't you put the beaker on the balance and zero the balance first? Yes, you can go into that detail. You can if you want, if you'd like. But essentially what they're looking for is measure the mass. You're measuring the mass using the top pan balance, aren't you? That's what you're doing. Breaking down every step of how you're doing that. Feel free to do it if you feel like you just want to cover yourself, absolutely. But the main point they want is measure the mass of the oil using the top pan balance. Okay. Cool. Okay, next question. Give one risk when using the equipment in figure 2. So out of all of these pieces of equipment, which one is going to be the most hazardous to us when we're using it, guys? What can you think of? Do I have any predictions? No, I don't have any predictions. This is just a kind of, in a way, our best guess of what we think could come up a lot. Yeah, so we're just covering topics that are very common. If you look at the top of this, that's why we're going through these topics in particular, but just trying to cover as much as we can. Best to keep yourself covered for all scenarios, guys. Burn from the heater, burning or scalding yourself from the heater. Exactly. Yeah, so getting burned by the heater is the main risk here. Correct. Well done, guys. And then it says, a different student did not have a joule meter and calculated the energy transfer by the electric heater. Use the physics equation sheet to answer these questions. Write down the equation linking energy transferred, power, and time. So this is one where you won't necessarily get this kind of question in your exam because you get the formula sheet, right? And all the equations are there. And it's telling you to use a physics equation sheet to answer this question. So this used to be a nice free question, but they're not giving these to you anymore. People have mentioned any sort of rearrangement of it is correct. So time equals energy over power, I see. Power equals energy over time, I see. And then you could also mention energy equals power times time. So I'm going to say E equals PT, power times time. Okay. You can mention it in word form or the symbol form, whichever one, and you'll get the mark here. Well done, guys. Very good. People have gone on to the next one. I look like I see the right answer there, so I'll keep going quickly. And it says, the electric heater has a power output of 50 watts. Calculate the time taken for the electric current element, to transfer 4,750 joules of energy to the vegetable oil. Okay, so what have we got here? Power watts, so that's a measure of power, so that's P. Calculate the time taken. Time taken is the letter T in our equation. And joules, remember we said already, joules is a measure of energy. So we know what P is and we know what E is. We don't know what the time is. So those of you that rearranged for T equals, excellent. So I'm going to put T equals energy over power, and then we just substitute our values. So 4,750 divided by 50. Some of you have put it, a lot of you have put it in the answers correct. It's 95. So that's the answer, 95 seconds. Again, that's 3 marks. If they said give the unit, it would have been 4 marks for the unit as well. Nice. Really good, guys. Good to see everyone's getting an answer. That's positive. You guys are doing well. Okay. A slight crossover from topic 1 into topic 2. So a little brief intro before we go into topic 2 here. It's saying, in a deep fryer, vegetable oil is heated by an electric heating element. Food is then cooked in hot vegetable oil. The deep fryer contains an electrical component, and food. Figure 3 shows how the resistance of the component changes with temperature. Okay, so you can see here resistance on the y-axis, temperature on the x-axis. Okay, and what it's going to ask us is what type of electrical component is it? People have dropped it in the chat. You can see as the temperature rises here, the temperature is increasing. If you go to the right, the resistance is falling. Yeah, so an increase in temperature is causing this resistor to decrease in resistance. Okay, and that correctly, as you stated, one that is a resistor that's affected by temperature or heat is a thermistor, otherwise known as a thermal resistor. Okay, as you can see, as the name suggests, thermistor, it's like a thermal resistor or a heat resistor. So that's the giveaway that it's that. Okay, I'm going to come back to this question because it's got a couple of topics that we're going to cover later. Yeah, so I'm going to go into that a bit more later. I want to get into this one, yeah, before we finish off for a break. Electric shock can cause the heater is electric. Potentially, you could mention that, Sarah. That is a potential answer. So yeah, good point to mention. But burn is the main one. But you could say electric shock because there's a circuit involved. Not doing triple content as well. A lot of you are asking. No, we have bootcamp recordings for all the triple content. So any of the small sections of triple. So there's, I know, a required practical extension on triple for heating up a fluid with a polystyrene cup, etc. That's in our bootcamp video. So please do check that out. And anything else like that will be covered in our bootcamp video. So do check that out. Do we have any tips for rearranging equations? So sometimes I mention this. If you check our notes, check the bootcamp and the notes we went through there, we often have triangles for equations. I always put, yeah. So for example, for the one we just did for power, if I scroll up, put it next to the equation here, we said E equals P times T, right? So I could set up a triangle like this, where E is on the top and the two what you multiply together are at the bottom of the triangle. Okay, and I split them all up. Reason being is, if I cover up the one I want to find, it gives me the equation for the other two. So say, for example, I want to find what's the time. I cover up time, and you can see here, that's energy over power. So time is energy over power, which we used here. That's correct. Yeah. On the flip side, if I cover up power, then we're left with energy over time. That's the equation for energy, for power, sorry. And lastly, if I cover up energy, power and time are like next to each other on the same row, so they multiply together. So energy equals power times time. So a triangle sometimes people find very useful for these. Yeah. So most equations it works for when you have like only 3 terms. But when it becomes more than that, you can't use a triangle. It's more just you just look at making it the subject in algebra like you would in maths. Okay. So onto this energy question before I finish off for our first break. So it says, in the sport called far leaping, an athlete uses a long pole to cross a river. It's like pole jump, but horizontally. Figure 4 shows an athlete far leaping. Figure 5 shows the athlete in different stages of far leaping. So you can see A, B, C, D, and E, yeah, from left to right. So we'll come back to that image. But here it says, complete the sentence for energy transfers here. So between positions A and B, the athlete speeds up. So there's an increase in the athlete's watt energy. So if it speeds up, We talked about this in our note when we were writing some notes earlier to do with speed and motion. What type of energy is increasing? Correct, kinetic. Yeah, so the athlete's kinetic energy increases. So we'll put that there. I'll cross out kinetic in the box. And it says, and decreases in the athlete's blank store of energy. So what other type of energy is decreasing as a result of that from this one? What do people think? Yes, people are dropping a bit of a mixture, actually. Quite a mix of answers. People have said elastic, people have said chemical, people have said GPE. Real mix. But I'm going to say the majority of people that I saw the answers for were correct. It's chemical, right? Because if you think about the person, we're talking about between A and B here. The athlete has just started, not moving, and then it's starting to run. So they're using energy to run, energy from their muscles into their legs to run. Okay, so that is energy as chemical energy that we store in our muscles. That's getting used up and transferred into kinetic energy. No gravitational because she's not changing height, and no elastic potential because there's no stretching or squashing involved. So the answer is chemical energy from her muscles. That is the chemical store that's decreasing because it's transferring to kinetic energy. So that is the transfer here. Okay? Hopefully that makes sense. Chemical energy, most that don't understand it, is energy stored as fuel. So for example, for a car, chemical energy is the petrol, the diesel that you put in the car. It's the fuel with which the thing works. The car works by fuel, isn't it? If you have no fuel, the car doesn't run. So for us, chemical energy is energy we store in our muscles, which we get from the food we eat. But it's energy store. It's an energy store to allow you to do stuff, basically. Okay. Between positions B and C, the athlete jumps to the pole and climbs up it. Which statement best describes the change in the athlete's energy between B and C now? Okay. So between B and C, you can see they're just running here, and then they're at the top of the summit of the pole in the middle there at C. So what energy transfers happened here? If you think about what we've discussed, people have mentioned it. Like height increases. Yeah, lots of people have said the height goes up, their position increases. So then gravitational potential energy also increases. It won't be anything to do with elastic because the pole is not bent at that point. It's at the peak. It's completely straight. It's not stretched or squashed. So it's not to do with elastic potential. It's to do with gravitational potential. And the fact that her height has gone up from B to C means her gravitational potential energy has also increased. So it's this answer here. Excellent. Well done, guys. Have we got more practicals coming up? Yes, there is one other big one at least coming up. There's actually three: two in electricity in topic 2, one in density and to do with density in topic number 3. So in our next 2 sessions, we're going to be having required practicals. Okay, the pole falls over from position C. The athlete lets go of the pole and lands at position D. The change in height of the athlete between C and D is 3 meters. The mass of the athlete is 50 kilograms, and the gravitational field strength is 9.8, and they're given a height, as we said, 3 meters. Calculate the change in gravitational potential energy between C and D, and use the equation GPE equals mass times gravitational field strength times change in height. Again, given to you in your formula sheet, you know this is EP, mass is M, gravity is small g, and height is small h. So we can see 3 meters is a change in height, so that's h. Mass of the athlete, that's M, and gravitational field strength G. So we've given all of these, and they want us to find the gravitational potential energy. So we just need to sub it in. 50 times 9.8 times 3, which is what someone has mentioned in the chat, and a lot of people have put the answer for 1,470 joules. That will be the answer here. Well done. Yeah, so it's an example of just using the equation, basically. How are people getting 1,470 and not 147? Because they did times by 3, maybe. That's what I've done, made my mistake in typing it out there. Because 50 times 9.8 times 3 instead of 0.3. Yeah, if you put 0.3, then you'll get 147. But if you times by 3, it should be 1,470. Okay, so the answer is 1,470 joules. Am I going through a higher tier? This is both. Yeah, it's foundation and higher tier. This is also a higher tier. Yeah, that's why. Okay. And the last one here, see, 3 marks because it wants you to give the unit as well, but they've given you a units to choose from, so you get a mark for this. Okay, but it says kinetic energy of the athlete in position D is 1,600. I'll underline that. The mass of the athlete is still 50 kilograms, the same athlete. Calculate the speed of the athlete in position D, and here they've given the equation and they've rearranged it already. The break literally going to be in literally 2 minutes. Okay, so I'm going to give a break in a minute. I'm just finishing this question and we'll go to our break. So they want us to calculate the speed. They've given us the equation for speed. They've literally arranged it for us. So we just need to substitute kinetic energy, which is here, EK of 1600, and a mass of 50 kilograms. Okay, so we sub that in. So speed equals the square root of 2 times our kinetic energy, 1600, over the mass of 50 kilograms. So if you put that in your calculator, can anyone tell me? Oh, I can see a few answers flying in already. People have said 8, correct. The answer is 8. And what is the correct unit? Meters per second. I see it from a few people. Okay, it's not joules per kilogram. Joules per kilogram is for specific latent heat. That's energy divided by mass. I can see why you said it, but because the square root of that is not quite right. Okay, so it's the meters per second. That is the unit for speed. Okay, it's the distance over time. So that is what it is. Okay. And then it says at positions A and E, the athlete is still standing still. Why does the athlete have less energy in position E than in position A, which is the correct answer here? Why do they have less energy at position E than in position A? Which is the appropriate one here? Some people are saying A. And someone says use chemical energy. It doesn't say that there, but the option is A, yeah, because they use the energy and it's being transferred to the surroundings. Think about it. She would have done some physical exertion, like when you run, you get hot and sweaty, transfer heat to the surroundings. Yeah, so energy has been transferred to the air. That is the correct answer. Athletes have a large power output when they are far leaping. What is meant by the power of an athlete? Think about the equation for power that we've dealt with. Remember we said, I put the triangle here, E, P, and T. I'll just zoom into it. If I cover up power, power is energy over time. Yeah. Which one best describes that out of these? Yeah, the middle one is to do with force, so it's not to do with that. The total energy transferred could be, but not quite, because it doesn't mention anything about time. Exactly. Someone mentioned it as in words as well about the rate. When you talk about the rate of something, that's over time. So energy over time, the rate at which they transfer energy is the power that they generate. Yeah, how much energy do they transfer and how quickly they do it. That's your power. Okay, then a second athlete crossed the same river by far leaping. The second athlete has less power than the first one when running between positions A and B. Complete the sentences. So the time taken by the second athlete, the one that has less power, the second athlete to run between A and B, would it be less than or same as or more than the first athlete? If they have less power, is there less power? Second athlete had less power than the first athlete when running between positions A and B. So their time taken, would it have been more than or less than? Or the same? Real mixed. Less power would mean it takes her more time. Yeah, so it's going to be more than. Yeah, the less power you have, the more time it's going to take you to transfer that energy. So more than is the correct answer here. Then it says the work done. Is that going to be less than or more than? This is an interesting point because work done is energy transferred. They're the same term. Okay, so I'm going to put that here as a note if you want to write it down. Work done can be interchanged with the term energy transferred. So if there's less power and power equals energy over time, if the power goes down, would the energy be more or less? The energy would be less than. Okay, the work done is less than because they're not putting in as much effort essentially. Yeah, the power you're producing, if your power is less, the energy you're transferring is going to be less. So the work done is less. Okay, that's why it's less than. Okay, fine. Someone said, sorry, I know someone mentioned to do the 5 marker. I'm going to leave it for a break now, okay? But I can quickly return to, when we come back to doing questions and I do electricity, I will come back to do this 5 marker for those that are interested, okay? Fine. Okay, guys, thank you for the first session. We're already 1/4 of the way through. You deserve a break. Yes, you do. 10 minutes, guys. So come back at 6:40, please, if you can. We're going to resume at 6:40 and we're going to go into topic number 2, so electricity. Okay, we're going to cover a few notes on that and we're really going to get into some questions on that. And I will finish on this 5 mark. I will come back to this 5 mark if I can as well, so people can understand it because it is a good one to go through. So I'm specifically going to focus on this one at the end of the session in the next one. Okay, guys, thank you very much. 1 hour down, 3 more to go. See you at 6:40. Thank you very much. Okay, welcome back, guys. Welcome back. Hopefully, some people got some food in between, a little snack or something. I know some people said they were hungry. I'm going to get there soon. But hopefully, you are refueled and ready to go for another section. Okay, so now we're getting into topic two. Topic two is all to do with electricity. So at the end of the last session, I mentioned I'll go back to another question. If someone has if you have a preference on a particular question out of the pack for topic two, do let me know so we can go to that one first and make sure we cover it. Okay. Okay, let's see what is covered in this section. Okay, so things that come up quite frequently: circuit diagrams and symbols. Yeah, or it tends to come up every year, especially in foundation. It does come up in triple as well, as you can see. So it does come up very often in combined and triple. Current resistance and potential difference comes up almost all the time. You're almost guaranteed to get some sort of question on it, whether it's calculation or description of relationship of like Ohm's law, etc. Resistors, again, you can see, look how heavily that is involved in combined. And then again, in the last few years in triple, you can see if that's come up a lot as well. And then energy transfers in everyday appliances. So this is like the equation we looked at for energy, power, and time, but using it on everyday appliances, your kettles, microwaves. They may incorporate a question like that, which I've put a question in this paper as well that you can look at. Okay, so important couple of things I want to look at as well is a couple of required practicals, okay, in this topic in electricity. I did mention it at the start. There are a couple of required practicals. But first of all, I'm just going to cover quickly a couple of important circuit symbols that are people tend to forget, okay, or get mixed up. So I'm going to put them here. You tell me what they are. You can obviously write them down if you feel free to. So go for it. There's one here. So a rectangle, but it's an arrow through it. And there's also one which is a rectangle with a hockey stick through it. What are the differences between those? Someone's mentioned resistor. A resistor is simply the rectangle itself. That is a resistor. But the arrow through it or the hockey stick through it makes it a different type of resistor. Okay. So the one with the arrow through it, you've mentioned it. Well done, guys, is a variable resistor. And the one with the hockey stick through it, that is a thermistor. Okay. So making sure you get those the right way around. So the hockey stick one is a thermistor or thermal resistor, as we mentioned, and one with an arrow through it is a variable resistor. Excellent. Okay. This applies to everybody. As you can see, what I saw earlier, it comes up in foundation almost every year, all the time. Okay. So definitely one to look at. Someone's mentioned it. I was going to do it next. But when you have a resistor, but the wire goes straight through it like this, it's one that people don't always get. It's a fuse. Okay. That's important. Ammeter and a voltmeter, they are used to measure potential difference in current. So you need to know those. Those are given by their letters. A for ammeter, V for voltmeter. Yeah. The other one I want to get that people get or don't know that much is this one here. It's like a play button in a circle like this. Does anyone know what this is? Who knows what this one is? A diode. People are quick to get in with that one. Very good. Yeah, this is a diode. Special property of a diode, it only lets current flow in one direction. Okay, very important that. Cool. The small difference with that is that you can get a diode, but it has arrows like this. What does that mean then? Very, very similar, but I've got arrows on it. People have jumped in. Excellent. It's an LED. In other words, a light emitting diode. The arrows are showing light being given off from the diode. So it's a light emitting diode. Well done, guys. Someone mentioned LDR. That is different. Okay. Again, if the arrows represent light, an LDR would have arrows coming into it because the light shining on the resistor changes its resistance. This is an LDR, light dependent resistor. So there is a difference there. Okay. So arrows pointing in means light shining on it. Arrows pointing out means it's giving off light. So light emitting. Okay. One other key one I want to compare is the difference between this and this. Having more than one. What is one singular one of these called and what is a group of them called? What's the difference? Excellent, guys. The individual one is called a cell. And then having multiple makes it a battery. Exactly. Anytime you have two or more cells, that means you have a battery. Excellent. On the battery or the cell, how do you know which terminal is the positive one and which one is the negative one? Short is negative, long is positive. Exactly. So essentially, if you thought about it, plus is made up of two lines. So if you take those lines and put them together, it becomes a longer line, doesn't it? Yeah, so positive means a longer line and the negative is the shorter line. Correct. Okay. The plus sign is not always on the left. They might reverse the connections. If they reverse the connections, it's going to be the other way around. So don't get caught up by just saying left is positive by default. It's the longer line that's positive. Okay, that's super important. So it's really good someone actually mentioned that. The long line is the positive one. Okay, cool. So that's a bit on circuit symbols. Now, someone mentioned what is the difference between alternating current and direct current, or alternating potential difference and direct potential difference. That is to do with the direction it goes in. If it's alternating means change. So it means it's constantly changing direction. If it's direct, it's only going one way. It's direct current going in one direction. That's the difference. Okay. So then one thing I wanted to get into next was Ohm's law. Okay. Can anyone tell me what Ohm's law is? Ohm is a measure of what, actually? What is ohms a measure of? That's important because that's what tells us what this is all about. Coming in, I think now a few people are saying it. Most people got it right. It's resistance. Ohms is about resistance. Okay, so ohms measures resistance. And the one thing that comes up in this topic about resistance, the topic is called resistance, potential difference, and current. It links all of those things together, is Ohm's law. Okay. Sometimes they ask you for the definition, but you do need to know what it is because it links to the equation you get in your formula sheet. And that is that the PD, or potential difference, across a component is directly proportional to the current through the component. Okay, to the current through it. Unless there is a physical change. Okay, and what do I mean by that is, like, for example, think of your fixed normal resistor, just a rectangle. If the potential difference increases, the current will increase. That's directly proportional. One increases, the other increases, and the graph you draw goes through the origin. Okay, so I'm going to go to our cheat sheets in a second and show you what the graph looks like so you're aware of it. But you can see for different graphs, when temperature starts to get involved as one type of physical factor, the graph starts to look different and you don't get that directly proportional relationship. Ohm's law doesn't get followed anymore. Okay, correct. Proportional or directly proportional as it goes through zero. Okay, so that's what Ohm's law is. What I want to look at now is, first of all, the required practicals, and then the graphs that I've just referred to. Okay, so if I go over here, you can see we've got a cheat sheet here for the required practical, the first of two. The first one being for investigating resistance of a component. Okay, so say we had a random component, a light bulb, or a random item, and we want to measure its resistance. This is the equation this is the experiment we're going to do. Okay, so in this example, it's resistance of a wire and how it varies with length. Okay, so you can see here we have a length of wire, but we connect it at a certain point, not all the way along yet, just the part of the way along. Okay, and we measure that distance to keep the length. Okay, so we use the crocodile clips to connect them, and that completes the circuit, right? And the important thing here to remember, ammeters you connect in series and voltmeters you connect parallel to the component. Okay, so that's super important. I'm going to mention that here. So I'll mention it in another color. Ammeter connected in series, and by in series I mean in line, right? So it's in line with the component. So in series, and then in another color I'm going to say voltmeter is connected in parallel. So that's again in a parallel line to the component. Okay, that's important. So when they ask you to draw a circuit, put in your circuit symbols in, make sure an ammeter is connected in series and a voltmeter is connected in parallel. Okay, cool. So back to here, I'll zoom out a little bit. So for this experiment, okay, you have crocodile clips, an ammeter to measure current, a voltmeter to measure potential difference, and obviously you need a battery or a cell to give you a power supply to generate that electricity in the circuit. Okay, so first of all, you connect the crocodile clips at a certain length, starting from 0. So you can see here we said 0. So starting from 0, connect the crocodile clip and connect another clip and change it every 5 centimeters. So you can see here, put the second clip at 5 centimeters. Then move the clip to a new length and record again. Yeah. So when you move the wire to the clips to a certain length of wire, you're going to get a recording on the voltmeter and the ammeter. Note those down. Then you increase the length from 5 to 10 centimeters, get the voltmeter and ammeter reading again. Then go to 15 centimeters, repeat again. 20 centimeters, repeat again. Yeah, so that's where this 0.4 comes in. Repeat for various lengths and record all measurements. Okay. And then lastly, from your formula sheet, and as indicated by Ohm's law, this is the equation. Yeah, you get in your formula sheet, V equals IR. So if we have V and we have I, remember I is for current. We get that from the ammeter and the potential difference in the voltmeter. We can sub in that to give us the value of resistance R of the wire. Okay. And what we notice is by the length of wire, as you increase the length of wire, the resistance is going up, and you draw a line of best fit. You can see it doesn't go through every point, but it matches the trend of points as best as possible, and you draw a line of best fit of your results. Okay, so that is the first practical for resistance. Okay, an important thing they mention as a way to make your experiment reliable. Remember, I said sometimes they'll talk about how do you make sure your experiment is reliable and accurate. They say disconnect the circuit between readings, because when the circuit is on, it gets warm. Think about any electrical appliance, your mobile phone, your PlayStation, your computer. Whenever you use it for a while, it's going to heat up. Yeah, and that's going to affect the results you're going to get. So turn it off in between for a little break for it so it cools down again, and then you repeat the experiment so you can get repeatable results. Okay. So that is for the investigating resistance in a length of wire. You can then get one where you're looking at resistors in series and in parallel. Okay. The name for the required practical is investigating resistance and length of wire. This is literally what the two I've got here. Investigating resistance and length of wire, investigating combination of resistors in series and parallel. So comparing series and parallel, there are a few rules, right? I'm going to mention them in our notes here. So someone wanted mnemonics. I saw a few mentions of mnemonics in the chat. I'm going to mention them here. So one of them for series, we put C reads like this. Yeah. And then for parallel, there's another one. So I'm going to come on to that. But first of all, the C is for current. Current stays the same in a series circuit. Anywhere you go in a series circuit, current stays the same. Yeah. And then the RI here is for resistance increases. The more resistors you put in series, the greater the resistance becomes. So resistance increases. Yeah, that's the general trend in series. Okay. Then for parallel, if you think about the word parallel, yeah. Also, no, I should do that in capitals because there's a way to remember this. So if I put parallel, you take the two L's here, they make a cross, L and L. Yeah. So they cross because current isn't the same. Okay. Current doesn't stay the same in a series circuit, it's shared. Current is not the same. Okay, so current is shared and potential difference stays the same in a parallel circuit. It's the opposite for series. Okay, that's one. The other thing I didn't mention in series is here. R is the only letter in series that, as we've written it, that has a loop in it. Yeah, because a series circuit is where everything is connected in one loop. Okay, so this is circuit connected in one loop. So in one loop. If I go to this one, I've got P, A, R, and A. They all have a loop in them, or complete a loop that's covered inside of it. So there's multiple loops. So in a parallel circuit, as we can tell then, there are multiple loops. You can have what we call branches. Yeah, so several branches or loops in the circuit. Okay, so those are the two rules that I'll zoom in. Apologies for those of you that can't see it. So series, that's one loop, everything connected in one loop. C for current stays the same, and RI for resistance increases. For a parallel circuit, there are multiple loops in the word parallel, so indicating multiple loops in a parallel circuit. And then the two L's make a cross, saying no, current is not the same in a parallel circuit. It gets shared. Okay. Again, this is both. This is higher and foundation. Okay. This is in both. So the reason I mentioned series and parallel circuits is because of the second required practical, comparing resistors in series and parallel. What do we do? So whether it's two resistors or three resistors, let's say two. Okay. What we do first of all, we get the recordings for one resistor. Okay, so we know how one resistor behaves. So connect the ammeter and voltmeter to the resistor. Remember, voltmeter in parallel. Look, you can see it's parallel to the component. whereas the ammeter is in series. It's in the same loop as the component. Okay, so connect those, record the potential difference in the current. Then, second step, take the resistor and add another resistor in series. So they're in line, they're in series now. Then record the potential difference in current. And then lastly, take that second resistor and move it from series to parallel, put it in a separate loop. So then we have the same recordings for one resistor, then two resistors in series, and then two resistors in parallel. Okay, and every time we do that, we can take a recording of the results and see how the current and potential difference varies between them. Okay, because in that we can use that information, use V equals IR, and work out the resistance. So this step here, step 4. And then you can see how the resistance varies from a single resistor to resistors in series and resistors in parallel. And what you'll find is, from our notes, series resistance will increase in series, and then it won't increase in parallel. It will actually go down. Okay, that's what we find as the difference. Okay, so that was one of them. Now, I was saying about graphs and how IV graphs look. We call IV for current against potential difference. Yeah, that's what IV stands for. So with that, we see that an ohmic conductor, one that obeys Ohm's law. Ohm's law is potential difference and current are directly proportional. What did we say about directly proportional? A straight line that goes through the origin. And that's exactly what we see here. Current and potential difference increase together, but go through the origin. Okay, so that is for an ohmic conductor. When there's a physical factor, though, that graph changes. Let's look at this filament lamp, for example. A filament lamp, like a light bulb in your house, when you turn it on for a bit and you put your hand near it, it's really hot. Yeah, so it starts to heat up. That is a factor that affects the way that this works. Okay, so you can see at lower current and potential differences, it kind of looks the same as an ohmic conductor. It's actually pretty straight, but then it starts to curve. It starts to curve here, right? And you can see, even though you increase the potential difference, the current doesn't increase as much. And eventually, it actually flatlines and the current doesn't increase anymore. Okay. Now, why is that? Because the filament lamp gets warm. If it gets warm in the circuit, the electrons start to vibrate. The electrons are the ones that carry charge in the circuit, right? But they vibrate. They start to collide with each other. They don't flow as smoothly, and you have a higher resistance. The current is struggling to flow. Okay. So then the increase in potential difference leads to a reduction in the current. Yeah, it doesn't increase as much because the resistance has gone up. So there we see the line flatten out. And that happens on both ends. Okay, the increase in current on both directions. When you reverse the current, you see the same trend. So we get this S shape. Okay, that's for a filament lamp. And the last graph you need to know is an IV graph. We spoke about it for a diode. A diode lets current flow in one direction. So you can see in the negative direction, nothing's happening. But when we go to positive, it then starts to increase. It switches on and then it lets current pass through. So that shows a diode allows current to flow in one direction. Filament lamp with low resistance obeys Ohm's law, exactly what I was saying. At low resistance, you can see it kind of does look straight, but then eventually it doesn't. So you can't say as a whole a filament lamp obeys Ohm's law because it is affected by temperature. Okay. Okay, then we spoke about in the previous question about a thermistor. We saw it in the question that we ran through in the last session. For a thermistor, when you increase the temperature and it gets hotter, the thermistor's resistance decreases. But this isn't proportional, right? It's non-linear, what we call non-linear, not a straight line. So resistance decreases as the temperature increases. And then the other symbol we referred to in the circuit symbols, a light-dependent resistor. When the light shining on it by these arrows increases, it causes the resistance of the LDR to go down. Okay, so that is important. So a lot of information to take in here. I'm just going through the last point that I want to cover, which is the second required practical, which is for IV graphs. Okay, so for those components that we just discussed, these three graphs, they may ask you in an exam question for a required practical, how do you find the IV characteristics of a ohmic conductor or for a filament lamp or for a diode? Okay, and these are the steps that you're going to take. You take your component, and whatever component that is, that's this green one here. Yeah, so you've seen I've replaced this on the right hand side. It could be a resistor, it could be a filament lamp, it could be a diode. Whichever one that is, put it here. Okay, and then you connect a voltmeter in parallel and an ammeter in series, just as we did before. Any circuit you're making, voltmeter in parallel to the component, ammeter in series. The key thing in this experiment that's different to the other ones is this here. You need a variable resistor. Okay, because that is going to vary the amount of potential difference that the component receives. Then you will be able to change the variable resistance and take some new readings. And you keep varying it to get multiple readings. Okay. So if I quickly read through this, it's going to tell us connect those components: variable resistor, ammeter in series, voltmeter in parallel. Then it says change the variable resistor, and that will alter the current and potential difference to the component. Yeah. So then you record the readings. And then you can do that at multiple readings at adjusting the variable resistor. Yeah. So every time you adjust it, take some new readings. That covers the positive side of the graph, for example. So to get the negative side, we then mention this next point: swap the connections. Super important. In the exam for this experiment, you want to swap the connections so you get the negative side. Okay, so swap the connections, and then you reverse the current's direction and record the results again. Vary the adjust the variable resistor, record the measurements. And then the last point, plot a graph. They want us to find the graph. You need to state you plot a graph of those points. Okay. Cool. So those are the experiments for electricity. Okay. 2/3. Two are in one of them, investigating resistance as the one required practical, and the other one is IV graph required practical. Okay. So those are the steps we need to take. Someone mentioned about summing resistance in series and parallel. So I'm just going to quickly cover it. In series, you just sum the resistors in series. Okay, that's all you need to know. To find the total resistance in series circuit, add up the individual resistors. In parallel, the thing you need to know is that the sum of the resistors is less than the smallest individual resistor. So what do I mean by that? Here, our three resistors are 6 ohms, 8 ohms, and 7 ohms. The total resistance of these three should be less than the smallest one. The smallest one out of these is 6 ohms. So therefore we say the total resistance is going to be less than 6 ohms. That is the way we remember it. Okay. So total resistance in series, you add them. Total resistance in parallel is less than their smallest individual resistor. That is the difference there. Okay. Let's get into some questions then. Yeah, so I want to try this in some questions. Let's have a look at how we get on here. So join me in this. Again, as we did before, really good answers. Keep joining in, keep answering, and let me know if you don't understand anything. I'll do my best to explain it again. A student investigated how the current in a diode varies with the potential difference across the diode. Figure 6 shows an incomplete diagram of the circuit used. Student measured the potential difference across the diode. Complete figure 6 by adding a symbol for the voltmeter in the correct position. How do we connect a voltmeter? Is it in series or in parallel to the component? Who can tell me? In series or in parallel? This is foundation, both. It's foundation and higher tier. Parallel, a couple of people, everyone's saying parallel. Yes, correct. Yep, parallel and parallel to the voltmeter. Okay, so you're going to draw it here. V for voltmeter. There we are, parallel to the diode. Okay, so 1 mark for the symbol for V and the circle, and the second mark for it being parallel to the diode. Which component should the student adjust to change the potential difference across the diode? So we just spoke about this in the practical. They haven't flipped it's not a battery, remember? It's a cell. It's an individual cell. And I did say you can have them either way around. They have the positive terminal on the long side. So that is correct. You can do that. So don't get caught out by saying that's wrong. Variable resistor. Very good, guys. Yeah. We were saying in the practical, adjust the variable resistor to give you new voltmeter and ammeter readings. So that's what you vary to vary the potential difference. Variable resistor is the one you change. Remember, an ammeter you're measuring from, so you can't control that. And this is your power supply. So you could increase the number, but having the same cell doesn't change the output there. The student measured the current 3 times for each value of potential difference. When the potential difference was 1.5 volts, the current varied between 0.95 and 1.08. This was caused by what type of error? So someone mentioned about errors in the session. I think I saw it in the chat. I wanted to save it for this question so you can understand what type of error this is. They've done the same experiment and they're just getting they've done it right, and they've done it right and got different values. Systematic is if there's an error in your way of doing it. It's random in this case because they've done everything right, but the result comes out different. Yeah, so that's random. You can't control that. You're not controlling it, and as a result, you're just getting different results every time. So this is random. Systematic is like a process error. So you're in the system, you're doing something wrong. Yeah, so something like when you're taking the recording, you did it differently the first time to the second time. That's systematic. Random here, we're doing exactly the same thing first and second time, but we got different values. That is a random error. Okay, that's the difference. For one value of potential difference, the measurements of current were 0.27, 0.32, and 0.31. Calculate the mean current. A bit of maths here. How does that go? Can anyone tell me the answer here? You want to find the mean current and average. There we go. Azim said you've done it, the right thing. Add them all up and divide it by 3. You add them all up, you get 0.9. Divide it by 3, guys. You've got it. Is 0.3. Okay. So for 2 marks, do show the working out that Azim had mentioned. I'm sure you guys all did it. That got the answer. So you add them all up, plus 0.31, divided by 3 to give you 0.3 amps. Excellent. 4 parts down, just like that. Figure 7 shows some of the results. Table 2 shows the results when the potential difference was greater than 1 volt. Okay, so it says at 1.25 you get 0.6 amps, and at 1.5 volts you get 1 amp. And it says complete the figure 7, plot the results, and draw a line of best fit. So that's what they're giving you 2 marks for. Okay, so if I go here and this exercise hopefully should be straightforward for you because you're just taking the points here. So 1.25 volts, you can see volts is on the x-axis. 1.25 is halfway between 1 and 1.5, right? So it's going to be in the middle here. So that's 1.25. And then it says 0.6 amps. And there is a current directly leading down the line, 0.6 amps. So that will go here. And then my second point, 1.5 volts. So we're here on the end of this line here. And then 1 amp, you can see that's also on the diagram. So 1.5 and 1, very much easier to plot. There we are. What type of line of best fit do we draw then for the second mark? How does the line look? Could you please explain the meaning of energy stores? So we did energy stores in the first section, strawberry cheesecake. So if you missed it, please do go back afterwards. But it talks about all the different types of how energy is stored. So depending on what type of energy, it's dependent on the type of action that's taking place. Okay, so that's something to take a look at. Go back in our video, go to our boot camps, and you'll get back onto that. A curve. Well done, everyone. Yeah, so don't get confused by trying to draw a straight line between everything. A line of best fit. Excuse my drawing here. Hopefully it's okay. It's not bad. It's not bad, but a curve through the points, essentially. Very good. That's going to be a freehand curve. Exactly. Yeah. Hopefully a bit better than me, because I would like to have gone through this point here, but I was close. Yeah, so drawing a freehand curve. Well done, everyone. Okay, moving on. Figure 7 shows that the relationship between potential difference and current for the diode is directly proportional, inversely proportional, or non-linear. Which is the correct one, guys? Are those bird noises in the background? Yeah, they are. They are. So I didn't know whether you could hear it or not, but they are pretty loud today. When should you draw a curve or a straight line? So a straight line is when you have a pattern that looks like it's a straight line. So for example, where do we have it? I had it in our notes here, like this. See here, it's showing a general trend of a straight line. Then you draw a straight line. Yeah, so you have to look at what the points are forming. In our question here, the points are forming a curve. So you take a curve. That's the difference. Non-linear, yes, for everyone. Everyone that said non-linear, you're correct, right? Remember, directly proportional was a straight line through the origin. Inversely proportional would also be a straight line, but a negative gradient. Non-linear is what I was saying, right? When we saw a curve, we call it non-linear. Okay. Exactly. Someone said it combined is part of triple. So that's what we do. We do covering all combined stuff, but obviously anyone that does triple, all of this is relevant to you. Anything specifically triple, I've mentioned it. Go to our bootcamp videos where we go through specific triple only content as well. Okay, the student adjusted the circuit so that the current in the diode was 1 amp. The student then reversed the connections into the diode. What happened to the current in the diode when the connections were reversed? Tick one of the boxes. Which one would it be? The current decreased to 0, the current remained at 1, or the current increased to 2? Remember what type of component we're talking about here. I'm going to underline it. It's talking about a diode. So connections are reversed in a diode. What would that mean? Some people said 1. Some people said 0. A lot of people saying 1. A few people saying 0. One person said 2. The correct answer is 0. Okay. The current decreased to 0. Remember, a diode, the special property, it only allows current to flow in one direction. Yeah. We mentioned the graph here. Let me scroll down. This is the graph for a diode. So it flows in one direction. When you reverse the connections, this is going to happen. You'll see absolutely nothing. So no current. So the answer is 0. Okay. Well done to those of you that got it. Hopefully it's a point for you all to remember that didn't get it right. It's fine you didn't. Just remember it now. Hopefully it helps you remember even more because you remember that you got it wrong. Okay. Excellent. So that's one. I'm going to skip this question for now. We can come back to it if we want. I'm going to go to the next one. Okay. To show a slightly different section of the topic. This one here, question 6. Okay, so figure 10 shows an electric whisk that plugs into the mains electricity supply. So here we are, something to do with an electrical appliance in the home. Okay. Why does it start rising after 1 in the diode graph? So because that's a good point. It doesn't start straight from 0. It's because it's what it has. It's called a switch on voltage. So it doesn't register that it's changed direction until it's gone a little bit into the positive direction. So then only it starts to increase. But they don't tend to ask you that's more of an A-level question. Okay, give 2 energy stores that increase when the switch is turned on. So someone asked about energy stores. This question is asking exactly about that. What type of energy stores increase when the whisk is turned on? So people have mentioned kinetic and thermal. Kinetic, I would absolutely agree with, is the first one that would have come to my mind because it's moving, right? The whisk is turning. The beater at the end, this is going to rotate. So you get motion. So anything with motion, energy through movement is kinetic energy. And then everyone also was right that said as you use something, it's going to heat up. Yeah, this kind of thing is going to heat up. It's an electrical appliance. Like I said, with your laptop, your computer, your phone, anything that all heats up, thermal energy is going to increase as you use the appliance. So those two increase. Excellent, guys. Really good to see everyone jumped in on that. So nice one. The next one here. Use the physics equation sheet. Again, this kind of question you're not going to get, but we're going to. It's more important in the next question. Write down the equation linking power, time, and work done. Remember, work done, I said earlier, was the same as energy transferred or energy. What would the equation that links power, time, and work done or energy be? There we go. Clay has got in there straight away. P equals E over T or P equals W over T. Okay, in this case, because they've mentioned W in the question, I'll refer to W. You're not completely wrong by saying E, but because they've talked about W in the question, use W in the answer. Okay, so P equals W over T. Amina, why is it not chemical? Chemical is a store that's used up. Okay, so battery or the circuit is providing chemical energy, so it's going to decrease when you're using the appliance. What's increasing is what you're outputting, kinetic and thermal. You're inputting kinetic chemical, so that's going to go down. In this circuit, actually, it's going to be electrical. Yeah, electrical is the input because it's plugged into the wall where current comes from. So that's electrical energy. Chemical is things such as food, someone's mentioned it, fuel for cars, etc. that I mentioned before. It's stuff that energy that gets things to work. It's your input energy, essentially. Sound could be given. You won't be necessarily wrong to give sound, but it's not a, let's say, like an energy store that one of the main energy stores that we refer to. So they tell you to ignore using sound. The main kinetic energy and thermal are one of the main types of energies. Yeah, so sound technically, I know you're going to hear something, but it's not the type of energy store they're looking for because you don't store it. It's like a wasted energy off to the surroundings. I know thermal is, but it's the main type. It's the main type of energy, and it goes into things, right? It goes into the other things in the surroundings. Okay, the power output for the whisk is 92 watts. Calculate the time for the whisk to do 23,000 joules of work. So we've got work, W, we've got power, P, and they want us to calculate the time. So we take our equation, P equals W over T. You then rearrange that, not WT, W over T. We then rearrange that to give us T equals P over, or W over P. Yeah, these two are going to swap because we want to find T, so we just swap these two around. Therefore, W over P. We're going to take the numbers that we've got there, 23,000 joules of work done, over 92 watts of power, and that gives us a value of 250 seconds, which a lot of people have got. This is both. Someone's asking if it's foundation or higher, it's both. And if it's combined or triple, it's both. Yeah, we're trying to cater for everybody doing their exam tomorrow, so we're covering both. 250 seconds. And that is your answer there. Yeah, 3 marks because it's 1 for rearranging, 1 for putting the numbers incorrectly, and 1 for the answer. That's where you're getting your 3 marks. Okay. Why won't we be asked a 1 mark question above it? Because now you're given everything in your formula sheet. So they found, unfortunately, they realized it is a free question, essentially, right? Because if you have the physics equation sheet and they're saying, what is this equation? You're just reading off a piece of paper, right? So unfortunately, they found that that is a loophole for an easy mark for people. So they've taken it out. Okay. Write the equation which links current, power, and resistance. This one's interesting. Again, it's given in your formula sheet. So that's why they don't ask you these kind of questions anymore. But this one is a different equation, okay? Slightly different in the sense that an equation for power, you'll find in your formula sheet, is one of two ways. Power equals current times potential difference. But then as we just saw from Ohm's law, V equals IR. Yeah, potential difference and current are directly proportional. That's where this equation comes from. So if I substitute that into there, P equals IR times I, which is I squared R. That's where this comes from. P equals I squared R. D. Loads of people got it. Excellent. Yeah. I thought I'd run through it, see who got it. Loads of people jumping in with the answer. Well done. Well done, everyone. And when they introduce that, it tends to mean it's going to come up in the next question. I think it is here. The current in the whisk is 500 milliamps. Current, I. Okay. The resistance of the whisk, R, is 640 ohms. Calculate the power, P, of the whisk. So we took this equation here. We're going to use exactly that. P equals I squared R. What are we going to do here? Someone's mentioned it exactly. One thing to note. Very, very important. Make sure your units are correct. Yeah. Milliamps is what's given here. That is not the standard unit for current. Amps is. So to go from milliamps to amps, you divide by 1000. Okay. So 500 milliamps divided by 1000 is the same as 0.5 amps. So we use that, which is 0.5 squared multiplied by the resistance of 640, which is like 0.25 times 640, or 640 times a quarter, which is 160 watts, which I saw loads of answers for in the chat. Well done, everyone. 160 is correct. Nicely done. Cool. Couple more in this question. The whisk has several settings that allow the beater to spin at different speeds. A faster beater speed needs a greater power input from the main supply. What is the potential difference between the live wire and the neutral wire in the mains electricity supply? So this is a general number that you need to know. It's a one marker, so it's just a value you need to remember. People have got the right answer. It's 230, right? Because the live wire is the wire that current flows through during normal operation of an appliance. The neutral wire is the one that just completes the circuit, so it has a potential difference of 0. The live wire carries this electricity, so it has 230 volts. So the potential difference is 230 minus 0, so 230. 230 volts. Okay, nice. Then changing the beater speed does not change the potential difference between the live wire and the neutral wire. The power input to the whisk changes because the current in the whisk changes. Complete the sentence here. When the beater speed increases, the current in the whisk increases because the resistance of the whisk does what? For 1 mark, we're looking for one word. Does it increase or decrease, or does it stay the same? When the beater speed increases, the current increases because the resistance goes up or down. Will the current need to be more or less for current to go through? The lower the resistance, the more current goes through. So everyone is correct. It decreases. Very, very good. Okay, so someone has asked, we're going to finish at, I'm going to aim for 7:30 on this one, okay? So I'm going to aim for 7:30 here. I'm looking at maybe trying to do 2 more questions. That 1-5 marker someone asked about earlier, because that's a really good question. So I want to check that with you guys. And then one of these questions. So this is an example of a practical, but I'm going to go to the practical above that. Let's see. The one I skipped earlier. Yeah, let's go with this one. Okay. So I'm going to pick some specific parts of this question, okay? So I'm going to do all of it, but remember, you're going to get the mark schemes at the end so you can have a look. How do you find the workbook? You should have got an email when you signed up to this. If you didn't get it, or you didn't get the email, sorry, send an email to help@flashrevisionlab.com and you'll get access to the email, okay? And you'll get the workbook through that. Are there triple questions in the workbook? Remember, triple covers everything. So every question in here will be triple. Yeah, it's just not triple specific, but everything in triple will be here. Go to our workbook, our boot camps videos to check for questions and content on triple. Okay. Body analysis scales use the electrical resistance of a person's legs to estimate the percentage of water in the person's body. Figure 3 shows the analysis scales, and it says the person's legs contain both solid tissue and water. A student uses resistors to model the solid tissue and the water, and the student connected a 20 ohm resistor in parallel with the resistor R. Figure 4 shows the circuit diagram. To determine the total resistance of both resistors, a voltmeter must be connected to the circuit. Complete figure 4 to show where the voltmeter needs to be connected. So similar, we had a question at the start where it asked about where the voltmeter should be. Who knows where the voltmeter should be connected? Someone said parallel to the ammeter. Do people agree, or do some people think something else? Someone said in between them. Some people have just said parallel, but we need to be specific to where. Parallel to where? Parallel to the label R. Very good. Yeah, it's parallel to the resistors. Okay, so you're going parallel here. You don't connect it in parallel to the ammeter because you're not measuring the potential difference of the ammeter. You put it parallel to the potential difference of what you're measuring. Okay, in this case, it's the resistors. So it has to be parallel to the resistors. Okay, cool. The student calculated the total resistance of the two resistors. The student's answer was 26 ohms. Explain why the student's answer cannot be correct for 2 marks. So we mentioned this. We mentioned this term as to why this would happen. Think about how are the resistors connected? Can anyone tell me how are the resistors connected here? How do you know where to put the voltmeter? I was saying it has to be parallel to the component that you're measuring. So in this case, we're measuring information on the resistor. So it needs to be parallel to the resistor. Sammy has got it. It has to be less than 20. Okay, because we said in our notes, and I'll go back to it, when we have resistors in parallel, the total resistance is less than the smallest individual resistor. In this case, the smallest one being 6. And up on here, it has to be smaller than 20. If 20 is the smallest, it has to be less than that. It's not going to be more than that. So the total resistance has to be less than 20. Okay, so to get the 2 marks here is one for saying it has to be less than 20, and the second one for the rule. It's not in series. It's not in series. Look at these 2 resistors. They're parallel to each other, aren't they? It's how the resistors are connected, not about how they're connected to the ammeter. The resistors are in parallel. Yeah, anytime you see 2 lines as a loop, you see another loop here compared to this loop. These 2 are in parallel. Okay. So the important thing here to get the 2 marks, I'm going to say cannot be correct because the total resistance, I'm going to say the total R, has to be less than 20 ohms. That's for 1 mark, and it says explain, so you have to give the why or the because. What is the reason for that? Okay, and the reason is because we said because the total resistance in parallel must be less than the smallest individual resistor. So that's how I'll explain the answer there. Okay, because that's the rule. Total resistance in parallel must be less than the smallest individual resistor. Okay. Is this AQA? Yes, it is. It is AQA. Okay, but remember, this is applicable to all boards, at least 70% of it, because the topics are going to just be largely the same and just in a slightly different order. Why can't a voltmeter be connected to an ammeter? Because remember, you're using those components to measure the component you're investigating. You're not investigating the ammeter, right? The ammeter is being used to investigate another component. In this case, we're investigating the resistors. So we're trying to get the potential difference in current of those resistors. So if we put this voltmeter here, we're getting the potential difference of the resistors. If you put your voltmeter here, you're getting the potential difference of the ammeter, which you have no relevance for. Okay, so no need. It's very important. You don't never put a voltmeter parallel to an ammeter. It's always parallel to the other components. Okay. Equation that links V, I, and R. We've seen that V equals IR, so I'm going to skip that. And then we're going to see this one about the investigation. Okay, so the student investigated how the resistance R affected the total resistance, the resistance of R, so the resistance of this resistor, affected the total resistance in the circuit. Okay, So how did that resistance affect the total resistance in the circuit? So you can see here, as this increases, the total resistance is also going up, right? So let's see, they've plotted it on the graph. And they say complete the figure, label both axes, and plot the remaining two values from the table and draw a line of best fit. I'm not going to finish it in this session because we've just got a few minutes left, but I want to talk through. Is the line going to be straight or is it going to be curved? Who can tell me based on the points on there thus far? Is it going to be a straight line or a curved line? Real mix of people saying straight and curved. More people have said curved, and it is going to be curved, okay? Because let's take, for example, we're missing 15 and 20 from the graph. So let's take 15 and 20. So 15 and 8.6, 20 and 10. Okay, so if I plot those 2 points, 15 and 8.6, so that's going to be 8.6. And then 20 and 10, that's here. Yeah, so you can see, like I said, when the points look like they follow a curve, draw that curve, freehand. So it's following a curve, right? They all flow through a smooth curve. So draw a curve here. If they were like scattergrammed like this, then draw a straight line through it. Yeah, but that's not the case that we have here. So let me undo that. They all follow a curve. You can see them follow through in a curve, so draw a curve. Okay. And then it says what resistance will give a total resistance of 4.4? We need to compare here, right? Resistance in ohms, 5 to 25. That's on the x-axis here. And then on the y-axis is total resistance. So then based off of that, you can take what resistance will give a total resistance of 4.4. You go to 4.4 over here, and then take your value here, which looks like 5, just above 5 or 5 ohms. Just above, actually, somewhere there. So 5.1 or 5.2. Okay, that's what we'll do there. Okay. Let's see this one, another error question. Let's see if you guys can get this. The body analysis scale initially shows a reading of 0.0 kilograms. When the student steps onto the scales, the reading is 64.8 kilograms. The student steps off the scales and immediately steps back on, and it changes to now 64.1. So it's changed. How has that changed? They said the difference between the two values is due to what type of error? Okay, seeing a mixture again of zero, systematic, and random. Remember last time I said you do exactly the same thing, but you get a different result. You did exactly the same thing here, but you got a different result. Same as last time. So same as last time, the answer is it's a random error. Because you haven't done anything differently. You stood off, stood back on. You stood off, you stood back on. You're doing the same thing, but your result is coming out different. And that is because it's random. Okay? So hopefully that makes sense to people. Okay. So we got a couple of minutes left. Well, let's finish this question. So apologies, guys, for the 5 mark. I haven't got to it yet, but I think topic 3, content's a bit shorter. We'll get through the questions, and I'll definitely come back to that 5 marker after that to revisit. Can I explain the error, Mohammed? So just as I said, when you do the same process, but you get a different answer, that's random error. When you do something wrong in the process, that's systematic error. Okay. So if he stood on 1 foot instead of 2 feet and he got a different value, that's a systematic error, right? Because he's done the process differently. Random error is you've done exactly the same thing, repeated it in the same way, so you should get the same result, and then you don't. That's a random error. Right, a break is going to be another 10 minutes again. Okay, so let's finish this question off. The total resistance on the student's legs is 600 kilo ohms. A healthy body water percentage is between 45 and 65%. The different measurements of the mass of the student mean the student could be in either category A or category B based on this graph. Yes, you can say 600 kilo ohms is what the person has a resistance of. That's what they've said, right? So if I draw that line up, they said they could be on either category A or category B. Okay. And they said healthy body percentage between 45 and 65. And they said the different measurements of the student mean that the student could be in either A or B. Evaluate if the student has a body water percentage that's healthy. Okay. So for 3 marks, let's have a look. If they said he's 600 kilo ohms and they said he's either in A or B, we need to look at what percentage he could be from A or B. Okay, so if I draw the lines, I connect them up. These are either somewhere between 60, 61% to this one square of 70, so I'm going to say 68%. Yeah, so 61 to 68%, I would say. Okay, so there you're getting 2 marks for stating what the value is at category A and category B. Yeah, so if in category A, his percentage is 61%. And then if in category B, his percentage is 68%. So we get 2 marks for stating that difference between them. Okay. And now they've said evaluate whether the student has a healthy body water percentage or not. Healthy ranges 45 to 65. So if he was in category A, is he healthy? Yes or no? You can tell me in the chat. Is A healthy and is B healthy? So A healthy or unhealthy, B healthy or unhealthy. Which ones is it? I see people saying yes, but I've offered both answers. Yeah, so someone's mentioned it. A is healthy because it's below 65. B is not healthy as it's above 65. Yeah, so you say if in A, they'll be healthy, and if they were category B, then they'll be classified as unhealthy. That's how you get the 3 marks. Yeah, so 1 mark for stating the percentage at each category, and then the last mark for stating whether they're healthy or unhealthy in each category. Excellent. Okay, this is foundation and higher tier. Okay, it's both, and it's triple and combined. Okay, we're going to leave it there. People have called it. It is right. We've gone just a couple of minutes over 7:32. So I'm going to say 7:42. 10 minutes, guys. See you back in 10 minutes at 7:42, where we're going to get into topic number 3, which is particles, changes of state, and density. We require practical coming up, the last one of this paper 1, and then some questions on this as well. Thank you, guys. Halfway there, halfway to go. Keep pushing through, guys. You're doing really well. It's all going to pay off for tomorrow, I promise. Let's keep pushing. See you at 7:42. Thank you very much. All right, guys, welcome back. Welcome back. We are past halfway. How are we feeling? Hopefully, everyone's feeling a little bit like they've learned something. That's the hope. Just keep something in your mind now, last minute bits of knowledge before the exam. That's the aim. Um, Hopefully, it's helping. We're on to topic 3 now. Okay, so topic 3 is on particles and motion of gases and things like that. So the key bits in here that come up very frequently, density of materials is a big one. It comes up for everyone. Look at it. It almost comes up every year. Yeah, in the past that we've seen, almost every year it's come up. So massive topic with a very frequent required practical in it, and one of my favorite memory tricks that Nina's come up with. So definitely going to go through that first. We then have internal energy, which again does come up in questions throughout the years, and can be quite tricky for people, mostly explaining. And then changes of state and specific latent heat, another one that does come up quite a lot. We spoke about specific heat capacity, but in this topic we talk about specific latent heat, and changes of state and states of matter is a big part of this topic. And then lastly, particle motion in gases, again, kind of linked to that. When we get to the gas state, how do particles move? Several 1 markers come up definitely for foundation and combined, and then a bit more explanation for the triple guys, but it does come up most of the time as well. Okay, as you can see there. So let's have a look. I'm going to start with the required practical for density of an irregularly shaped object. So let's say I had a random rock and I wanted to find the density of it. What is the experiment? So I'm going to put here, let's zoom in a bit, density required practical. Now, the memory trick is to do with the Eureka can. Yassina's come up with it. Yes, my favorite memory trick of all time, me face. MEFACE. Okay, what does everything stand for here? We'll go through one by one on these. So M for mass. We need to find the mass of the substance that we're measuring. So measure it using a top pan balance or a mass balance. Yeah. So mass of object. That's the first one. The you've all mentioned it. What is this for? Best practical ever. Yes, it is. I mean, purely for this memory trick, I think it is. So the memory trick has made it for me. But yeah, it is a good practical. E is for the Eureka can. Okay, so we're using the Eureka can. What is that? It's like a beaker, but essentially with a spout on the end of it. Yeah, that should be more flat. Sorry, and a spout on the end. You fill it up to the spout so that when you drop the object into it, the level rises, and the liquid that you've displaced, moved out the way, falls out of the spout, and you collect that liquid. Whatever comes out is the volume of the substance. Okay, so it's certainly possible the Eureka can will come up exactly why we want to cover it. Okay, this is exactly why we're doing it. Everything we've done today, the exact reason why we're doing it is because we think these are the things that come up a lot of the time. So we just want to keep you prepared for as large amount of it as we can in the day before the exam. Okay, the next thing then is fill. So after the Eureka can, we say we fill the Eureka can, like we said, up to the spout. Then we add the object. Yeah, so we add the object in. So that's add, and that causes a displacement. And then we say C for cylinder, measuring cylinder. Okay, so by that I mean we put a measuring cylinder on the end here, and then we collect that liquid, so we get the volume. We now have the mass from the first stage, and from the cylinder we get the volume. And the last point is equation. We take the equation for density. Again, it's given in your formula sheet, but density equals mass over volume. Okay, so who can tell me what the unit for volume is? Is it possible that it will come up? Yes, Alexandra, that's what I just said. It definitely could come up. What we're covering is all in the syllabus. So this is all things that could potentially come up, which is why we're going through it. Yeah. So C is measuring cylinder. Yes, it's just a memory trick for it. It is called a measuring cylinder. That is correct. Yeah, we're just giving you this tip as a way of memorizing it. What cylinder is it? It's a measuring cylinder. That's correct. Lots of people have put centimeters cubed. Careful, that is not the standard unit for volume. Okay, the standard unit for volume, it's good I mentioned this, it's meters cubed. Okay, that is the standard unit for volume. For mass, we've seen it already. I've asked you it before. The unit is kilograms. So what is the unit for density, guys? Exactly. You could say methane if you want to remember it as measuring cylinder, but my face because of the face. If you guys have seen it, if you haven't seen it, go and check it out on our TikTok. Nina's done a fantastic video, and seeing his face on there cracks me up every time. So it's a great way of remembering it. You did such a good job on it. So yeah, please do check that out. And yeah, I see everyone's put it kilograms per meter cubed. Yeah, that is what the unit is going to be for density. Okay, that is the standard unit for density. Excellent. So it's so nice because see you can summarize a 6 marker, and I've never seen one so good where you can summarize 6 marker in like 6 lines of paper. So yeah, really good to use that as a memory trick for the required practical for density. Something that comes up quite a lot, density. So good to know. Okay. Excellent. So that was for density. The next thing, as I put in my frequency of topics, is internal energy. Okay. So I just want to mention the point of what internal energy is. So any substance of any state has an internal energy. Okay. And basically, it's the sum of all the potential and kinetic energy of all the particles. Yeah, the sum of all the kinetic and potential energies of the particles in a substance. So that's what I'm going to put here. It's just a note for reference. It's a question that sometimes comes up asking you for the definition of it or asking about how internal energy changes. So to know that, you need to know what it is, right? In order to know how it changes. So I'll put the definition here quickly and explain how that then changes. Okay. So it's energy, potential energy. I see someone's asked, what is potential energy? Potential energy is like gravitational potential. Yeah, so energy due to the position of the particles. Okay, and how they're positioned. How much potential energy they'll have is based on their position. So it's the sum of the kinetic and potential energies of particles in a substance. Energies of particles in a substance. Okay, so that's what internal energy is. And if you think about the different states now, okay, so we're thinking solid to liquid to gas. So I'm going to go to our cheat sheets and I'm going to go to ones for changes of state. So we can see that and I can explain these changes in state. Okay, so if we go to this here, okay, very to know this, what the different state changes are. Okay, if we go from solid to liquid, we think about it. Solid particles are very fixed in their position. Okay, but then when they become a liquid, they're still in the container, but they can flow around a bit more. Think of your water bowl. It fills up volume of your water bowl, but as you tip the water bowl left and right, the liquid moves around, right? It has more freedom to move. Okay. With that, more movement means more kinetic energy, right? So the kinetic energy increases. Their positions can also change, so their potential energies increase. So therefore, internal energy increases from left to right. Okay, as you go from solid to liquid to gas, the internal energy will increase. As you go the other way, it will decrease. Okay, because less movement and they're more fixed in their position, so their potential energies are fixed. Okay, so that is the case for internal energy. It increases as it goes from solid to gas. Okay. Let me see. I think I mentioned the point here. There we go. Yep. Low internal energy for solids, high internal energy for gas. I'm going to make that point here as well. Internal energy increases from solid to gas. Okay, so we know the other way is going to decrease from gas to solid. Cool. So that's internal energies. Okay, so we're going to see some bits on that as well. Then the other big thing I want to look at is changes of state and specific latent heat. Okay, so when we mentioned about those changes of state, we covered that bit. But what is specific latent heat or latent heat? When we talked about specific heat capacity, that was energy to increase the temperature of a substance, right? E equals mc delta theta. But here, specific latent heat is energy used to change the state of a substance. Okay, so as I put here, the energy required for a substance to change its state. So instead of the energy being used to increase the temperature, the energy is being used to increase or change its state. Okay, so when you're heating something up, if I go here, when you're heating something up, as it's warming up or its temperature is rising, it's heat capacity that's involved. That's what's on this side. Yeah, specific heat capacity is for temperature change. Specific latent heat is for state change. And when the state changes, you're not increasing the temperature. So you'll see a constant temperature because the energy is being used to change the state. Okay. So you can see here when you heat and cool down a graph. Okay. So if heating and cooling graphs, I'll zoom out a little bit. Heating graphs, as the title suggests, the temperature is going to go up. Yeah, but the points at which it doesn't change temperature, you get a change of state. Firstly, from solid to liquid, you get a straight line at melting. The temperature doesn't change because the energy is being used to change the state. Okay. Equally, with the next state from liquid to gas, energy isn't being used to change the temperature; it's being used to boil the water. Okay. So that is for increasing. The same thing you'll see when you're cooling down, when you go changing a state from gas to liquid, the state energy is being used to change the state. Okay. And from liquid to solid, no temperature change. Very, very important point. Okay. So I'm going to put as a note here in our notes, you can put this if you like. Temperature does not change when changing state. Okay. That's that. And now the last point I wanted to make on this section before we look at some questions to test us on this a bit more: particle motions in gases. Can someone give me one word? There's two words I'm looking for. One in particular to describe the motion of gases. What word will people say describes the motion of how gases move? Excellent. Random. Yeah, in all directions. So they have random directions and random speeds. Okay. So I'm going to say gas particles move at random speeds in random directions. So the one word to describe it, as you've said, is that it's completely random. Yeah, there's no trend to how they move. They move very erratically of their own accord. Random. Okay. Excellent. So we've covered some of those points. I want to see some questions now that we do together, just so we can make sure we understand a bit more, and it will kind of prompt a few more points that are key that we might see in questions. Okay. What about liquids? Liquids aren't completely random, right? Their movement is dependent on the container that they're in. So they'll move depending on the size of the container, how they move. The particles slide over each other, kind of more in unison than gas, right? Not as random. So, and solid is the least random. Yeah. So if I go to different states, again, go to our cheat sheet here. Let me go to this structure of particles. Look at them. So for a solid, very rigid, right? Can't really move very far. Fixed vibrations, not very random. Here, in a liquid, they can flow a bit more, so it's a little bit more random, but then gases is totally random. Yeah, so you can see for liquid, we've put the motion or arrangement is random, but still close together. Okay. But then gas is completely random and far apart. Yeah. And as you go from solid to liquid to gas, the density is less. Gas is the least dense. Okay. And that's what we compare between the three. Okay. The bonds in solid are super strong, but that's why when we heat up the substance and melt it, we break those bonds. The temperature doesn't change, but we break the bonds in it and it makes it weaker, and then it becomes a liquid. It then weakens again when it becomes a gas, which is why the bonds between forces between the particles are very weak in a gas. Okay. All right. Let's on this then. So here we are. First off, 6 marker off the bat. Okay. A student wanted to determine the density of the irregularly shaped object shown in figure 3. So it looks like a knight on a chessboard almost. Plan an experiment that would allow the student to determine the density of the object. So it's an irregularly shaped object, right? That's the key thing. If it was regular, and this is what I didn't mention actually, if it was regular, the experiment becomes easier, right? The whole Eureka can method is because the shape is irregular, so you can't measure the volume in a standard way. If it was regular, you can just measure the lengths of the sides and calculate the volume. So here, people have got it. My face is the example, okay? We're literally spitting out what we said on my face, and that's what I put here, okay? So you'll see 6 points. Measure the mass using a mass balance. So remember, as you're doing the method, mention the equipment as well, the apparatus. Yeah, so mass balance as well. Next step, me face, E. Yeah, fill a Eureka can up to its spout. So really, we've covered M, E, and F, Eureka can and fill. Yeah. Then A for add. add the object or place the object in the Eureka can. Then, once we've added it, me face AC, C for cylinder. Yeah, so measuring cylinder. So collect the displaced water from the Eureka can using a measuring cylinder. Yeah, so I stopped underlining, but I will keep underlining all the points we mentioned about equipment. Eureka can, measuring cylinder, mass balance. Yeah, we're mentioning all the pieces of equipment that we're using. So MEFAC, me face, E, the last point, calculate the density using the equation rho equals mass over volume. And there we go. Yeah, I've literally spewed out the face mnemonic and used it to get 6 marks, and I've barely used 6 lines as well. So really, really good question. I think if it came up, I would be super happy if I were you, just because it's the easiest one. The electricity ones are a little bit harder. I know, I can understand that, but this one is a really, really good one. So fingers crossed for you guys that it does come up, but it's okay if it doesn't. You just, as long as you know how density works. Okay, what sublimation? Sublimation is when the state changes directly from solid to a gas. Prime example of that is a glacier. So in the Arctic, the glaciers, you can see that there's smoke or steam coming off of it because it's turning straight into a vapor as it leaves the iceberg. So then it's going straight from gas to solid to gas. Sorry. What was the acronym for the specific heat capacity one? I kind of made it up off the top of my head. It was called MATES. So because it was talking about what we're measuring, so mass and temperature. E for what did I say? Mass and temperature. Oh, it was good. Can anyone remember what I said? Mass and temperature. It will be in the notes. Go back to it, and I've written it. I'll try and make a video out of what it was. It wasn't equation. It was something, and then S for specific heat capacity. But yeah, mates was the way I did it. Energy. Thank you, guys. Thank you very much. Good. Guys are paying attention even more than myself. But yeah, very good. Yeah, mass and temperature, energy, and then specific heat capacity. That's what the things you need for that. Are we going to do half-life? Yes, we are. It's in the last topic, so bear with me. We're on topic 3. Topic 4 in our final session. So in about half an hour, 40 minutes, we'll be into that. Okay, so we're almost there. Keep pushing, and we'll get there. Okay. Cool. So the next question. Another student did a similar experiment. He determined the density of 5 common plastic materials. Table 1 shows the results. Figure 4 shows the results plotted in the bar chart. And it says, complete figure 4, write the correct scale on the y-axis and draw bars for polystyrene, polyester, and PVC. So basically the last 3 they haven't plotted on the graph. The key thing we need to do, though, is get the scale correct. Okay. And you can see here, acrylic is 1200 and nylon is 1000, sorry. Nylon's probably the easier one because it's 1,000. It's a very round number. So we can look on the graph here and see 1,000. This should be 1,000 for nylon. Okay, so that's how many large squares? That's 1, 2, 3, 4. So 1,000 divided by 4 means each big square is 250. So I'm going to go with 250, 500, 750, 1250, 1500, and 1750. Yeah. So every big square is 250, and each of those squares is made up of 5 individual squares. So 250 divided by 5, each one is just 50. So I'm going to leave it at the bottom there so we know each increment of square is 50. Then based on that, that's what we can use these for. Okay. So what you can do is divide each of these by 50 and get the number of squares. So I'm going to put in my calculator. 1,380 divided by 50 is 27.6. So for polyester, I'm going to have to go 27.6 small squares up. Yeah, so 5, 10, 15, 20, 25, 27.6. So somewhere up here. Yeah, and match the width of this. Each of these are 4 squares wide. So I'm going to go 4 squares wide. Like that. And like that. Yeah, so that's polyester. Polystyrene, 1040. So 1040 divided by 50. That's 20.8. So 20.8 squares. So 5, 10, 15, 20.8. So it's going to be somewhere here. 20.8. I've made the square too big, but yeah, there we go. 0.8. That's not straight. It has to be straight there like that. 20.8. Okay, and the last one, 1100, which hopefully this should be more round, divided by 50 is 22 squares exactly. Yeah, so 5, 10, 15, 20, 21, 22. So there. And there. 22 squares high. And now we've matched it up. Perfect. That's how we do it. Okay. So once you get the scale, it becomes easier to follow that scale to do the rest. So just wanted to show you how you get them. It's 4 marks that. So that's really, really, really good question to get 4 marks on. Yeah, as long as you get the scale right. Okay. Uncertainty is mentioned here. So some people are talking about errors and uncertainties and stuff. So I'll come on to errors again a bit later on. Someone asked it. I will cover that. We talked about systematic and random, but not about zeros. I think people asked about zero error. I've bear that in mind. So bear with me. A student is given a piece of different plastic material. The student determined the density of the material 3 times. Table 2 shows the results, and it shows 3 different values. Yeah, so 960, 1120, and 1040. Determine the uncertainty. So when you give this how do you give the uncertainty when you get a variety of results? Frozen, good to see you, and you've jumped straight in with the correct answer. Nicely done. The range of the answers divided by 2 is the uncertainty here. Okay, that is how we do uncertainty here. So when you have a range of results, uncertainty equals range divided by 2. So the range being the difference between the smallest and largest value. Largest being 120, smallest being 960. So we find the difference between those and simply divide it by 2. So 1120 minus 960, that's 160. So divide 160 by 2, it gives us a value of 80. And there we are, 80 kilograms per meter cubed is the uncertainty. And you can put plus or minus if you like in front of it, plus or minus 80. Well done, guys. Yeah, so that's how you do it when you get more than one value. When you have 3 or 4 values, find the difference between the range between the largest and the smallest and divide it by 2. That's the uncertainty. Okay. This is mixed, Fabio. Exactly. This is mixed. Yeah. So we're doing it to cover for everybody and cater for everyone. Okay. Figure 6 shows a swimmer. This question. Let me see. I just want to see what other bits are in here. Drawing axes again, which we've covered. Materials. Mass and volume. Couple of equations here. What are the equation bits? And then we'll do this question 5. And this question 5 is a bit better. Oh, also this is good. That's got specific heat capacity. Yeah, okay, fine. I'm going to pick a couple of questions from here. Let's see, we might be able to get through most of these actually in this session. So let me go with, I said here. Okay, so I'm just skipping to this question, okay, because it's something to do with a specific latent heat. Okay, so it says, during the investigation, 0.015 kilograms of the ice melted. The temperature of the water and the ice did not change. Yeah, remember I said when you change state, the temperature doesn't change. So it's indicating that. The specific latent heat of fusion of ice is 334,000. Calculate the energy needed and use the equation. Energy to melt the ice equals mass times specific latent heat. Okay, so they've given us that. You'll see it in your formula sheet. The equation, the letter form of it is E equals ml. Okay, so M, the mass, we've got 0.015. L, they've given us 334,000. So we just substitute those in. E equals 0.015 times 334,000. Everything is in its standard units. So what would the answer be here? It is combined higher, correct. Someone said that. It is combined higher, combined foundation. It's in both. 5,010, people are getting it. 5,010, very, very good. It would be better if I didn't rub it out. And there we are, 0.15. That's 5,010 joules. That is the energy required to melt this mass of ice. Yeah. For uncertainty, it's better to put plus or minus, I would say. Yeah, to cover yourself, better to put plus or minus. But sometimes they'll ignore it. Yeah, so worst case is they'll just ignore it, but you won't lose marks for putting it. Don't put just minus. Absolutely not. Yeah, but if you put it, they may ignore it, but that's why I'd say just put it just in case if you like. Okay. So you got 5,010. The next thing is like a practical question. Let's see if you guys know what this is. So the student wanted to determine the density of the wetsuit material. The student measured the length of one side of a cube of wetsuit material with a micrometer and with a ruler. So you can see here, the results on the micrometer have more decimal places than the ruler. And it says complete the sentence. The results show that compared to the ruler, the micrometer has a higher what? What would you say it is? People have said it. Resolution. Very good. Yeah, resolution is like the lowest value that you can read to, the smallest increment that you can read to. So a micrometer is more has a greater resolution. Correct. And then it says use the equation sheet to get the equation for density. I'm going to do that because we're given it in the formula sheet. So I'm going to keep that there. Density equals mass over volume. Says the student calculated the volume of the wetsuit was 0.186 centimeters cubed, and the density of the cube was 0.3 grams per centimeter cubed. Calculate the mass. Give your answer in grams. So here it's different, right? Usually the standard units for volume is meters cubed, but they're given centimeters cubed. And usually the standard unit of mass is kilograms, but they've said give your answer in grams, and they've given density as grams per centimeter cubed. So how do we do this, guys? Or can someone drop an answer in the chat? Density equals mass over volume. They want us to find the mass. So what will we do for maths? For math, not maths, mass. Someone's got 0.0558. We'll see if they're correct. Mass, you rearrange. We want mass on its own, so we multiply both sides by volume. Mass equals density multiplied by volume, or rho v. Substitute our values. It's not in its standard units, but grams and centimeters cubed link like kilograms and meters cubed. So here's an interesting question. We do not need to change the units. So we just do 0.3 times 0.186. And those of you that mentioned it, you are correct. 0.0558 grams is the mass of the cube in this case. Yeah, people got it. Nice. I've mentioned conversions earlier, but I saw it. So when we come up with equations with conversions, I will show you when they're needed. In this case, it is not needed. Yeah, so there's a rare occasion where the units aren't your standard ones, but the conversion isn't required. Okay. Data storage computers get very hot. Scientists investigated using the sea to cool data storage computers. The computers were set up inside a large metal container. Figure 8 shows a metal container before it was lowered into the sea. Why is the container made of metal? Someone has said A. Are they right? Metal is a good high conductivity. Metal is a good thermal insulator, or metal is a poor conductor of thermal energy. Metal isn't a poor conductor, right? We know it conducts heat, it conducts electricity. So therefore it's not a good insulator. So the only one that's correct, you all have said it, it's A. Metal has a high thermal conductivity. Right, so the question I wanted to come to was this one. The wall shows the containers. The walls of the container are solid, Figure 9 shows the arrangement of 6 particles in a solid. As you can see, fixed and rigid, as we showed before, all touching each other, don't really move, fixed together. The air inside the container is a gas. Draw the arrangement of 6 particles in a gas in the box below. So how are we going to do this? Can anyone tell me? If it's 6 particles, where are they going to be? All spread out and in random places. Well done, everyone. Yeah, they move fast, but we don't have to show the motion. They want the arrangement only. Yeah, they've said arrangement. So we're not mentioning the speeds. Whilst you might be correct, they're moving randomly and at different speeds and could be very fast. The arrangement, how they're positioned. Yeah. So as long as there's no pattern, it's quite fun. You're just drawing 6 circles any way you like. And unfortunately, I've made that look quite even. There we go. Yeah, something a bit random. 6 particles all over the place. Excellent. How does the air in the container exert pressure on the container? Okay, so this topic talks about pressure. Anyone know what the equation for pressure is? You don't need to remember it, but it helps you with defining it, what pressure is. Does anyone know what the definition of pressure is? Everyone that has mentioned it has got the answer right. Yeah, air particles collide with the walls of the container because pressure, and now people are saying it, force over area. Yeah, by definition, pressure is the force per unit area on a surface. Okay, so the particles, they collide with the air container more. They're applying more force onto the walls of the container. More force on that area means a greater pressure. So the pressure increases. Yeah. So exerting pressure means they're colliding with the walls, applying force to the walls of the container. Excellent. This is AQA higher combined, correct. AQA higher and foundation combined. Okay, as the container is lowered into the sea, the temperature of the air in the container decreases. Complete the sentence. When the temperature of the air in the container decreases, the average speed of the particles does what? So this is the topic again about motion of particles. If the temperature decreases, what happens to the motion of particles? Excellent, everyone. It does decrease. Why is that? Because remember, same as when we talked about electrons in topic 2, an increase in temperature gives you more energy. More energy means more kinetic energy, more vibration, more movement. Okay. A decrease in energy means less kinetic energy. Yes, and you've got it as well. That is why it's directly linked. Temperature and kinetic energy are directly linked. So the lower the temperature, the lower the kinetic energy, and therefore the lower the speed. Okay. After the temperature of the air in the container had decreased, the computer switched on. The computers caused the temperature of the air to then increase. Describe how the air pressure in the container changed as the temperature decreased and then increased. So, for 2 marks, it then decreased and then increased. So we need to mention what happens to the pressure when the temperature decreased and what happens to the pressure when the temperature increased. Correct, Marshmallow. Yeah, it follows that same pattern. Yeah, because of what we just said. So I'll break it down. When the temperature decreases, the first part of the question, what happens to the pressure? The temperature decreases. As we said in the previous question, the speed of the particles decrease. If their speed is less, that means they collide with less force, less powerfully on the walls of the container. Less force on that area means a lower pressure. Okay, so for the first mark, we say as the temperature decreased, the pressure decreased. Then for the second bit, it says, and then increase. So as the temperature increased, we're doing the exact opposite now. The particles gain more energy. They vibrate more. They have more kinetic energy. They move faster. The faster they move, the stronger the force of their collisions, the greater the pressure. So as the temperature increased, the pressure increased. That's all you need to say for the 2 marks. So when the temperature decreases, the pressure increased. And then when the temperature increases, the pressure increases. Exactly. People are mentioning it. The bits about explaining about frequency of collisions and pressure, that's more triple. But explaining this relationship, that's for everybody. Okay, so pressure decreases at a lower temperature, increases at a higher temperature for a fixed volume, like this container, where the container is fixed. Okay, next one. The container has a length of 2 meters. It has a cross-sectional area of 7.5 meters squared. Calculate the volume. So it's a very simple maths question. And they've told you the equation even. Length times cross-sectional area. They've given you length and cross-sectional area. So this is kind of a gift of a 1 marker almost. Yeah, volume equals length of 12 times 7.5. Who can tell me what that answer is? It should be 90. Exactly, guys. 90 meters cubed. Everything is in meters and meters squared, so no conversions required. Just a simple substitution. Excellent. And then write down the equation that links pressure, density, mass, and volume. Again, comes in your formula sheet. We've seen it earlier, so I'm filling that in. The average density of the container and its contents is 1100. Calculate the mass of the container and its contents. So density equals mass over volume. Again, we want mass. So we rearrange, right? So multiply both sides by volume. Mass equals density times volume. Density of 1100. The volume from our previous question of 90. What is the value for our mass here? Anyone know? Our whole thing finishes at last break in about 14 minutes, and then we'll break one more time before we get into the last section. Excellent. Yeah, that is the mass. Pretty heavy, right? Substantial container with a substantial mass of air in it, 99,000 kilograms of it. Okay, on to the last question of this section, and then I'll go to someone is asking for a 5-mark calculation. I did have one earlier, so I'm going back to it. I'll stick to my promise, hopefully. A piece of steel is heated until it is all melted. Calculate the change in thermal energy when the temperature of the steel is increased by 50 degrees C. So what's it says the mass of the steel, M, is 4 kilograms. Specific heat capacity of the steel, C, is 420 joules per kilogram, degrees Celsius. And this is increased by 50 degrees. So that's your delta theta, your change in temperature. Yeah, so we've got the temperature change, we've got the specific heat capacity, we've got the mass. And this calculate the thermal energy. So we simply substitute them in. So 4 times 420 times 50. So what's the value for that? 84,000. Yep. Well done, everyone. Those of you that got it in the chat. Well done. 84,000. Very good. Then the internal energy. So I mentioned this, right? Let's see if anyone can remember. The internal energy of steel increases as the steel is heated. What is meant by internal energy of the steel? What did we say it was? What is internal energy made up of? C has dropped in very quickly. Good to those guys that are paying attention. Yeah, well done. C is to do with internal energy is the sum of the total kinetic and potential energy of the particles. In this case, they've said the steel particles because it's the steel that we're talking about. Very, very good. Nice one, guys. Okay. So solid steel cannot be poured. Which statement about the particle in a solid give the reason why? Think about the structure of a solid. I'm going to do a 5-mark calculation, Janet, not a 6-marker. I have a 5-marker from it earlier. I'm going to have it here. So keep an eye out in about 5 minutes. We'll move on to that one to finish this session. The particles are in fixed positions. Everyone has put C, correct. That is the structure of a solid, right? So if it's fixed, they're not going to move anywhere. So they're not going to flow and pour like a liquid because they're all fixed. Very good. And the blank here, as the piece of solid steel melts, the mass of the steel decreases, increases, or stays the same. What is correct here? So I've got stays the same and I've got decreases. Which one is correct? Mix, actually. But the majority have got it. It stays the same, okay? Because the mass isn't going anywhere. It's just changing how the mass is sitting. Instead of a solid, it's now a liquid. Yeah, so instead of 20 grams of solid steel, it's 20 grams of liquid steel. Still 20 grams. So the mass stays the same. Important one there. Yeah, so when they change state, the amount or the mass of it, the mass is conserved. Exactly, Denise has said it. Yeah, as the state changes, mass is conserved. Okay. Which diagram shows the arrangement of particles changing when a solid becomes a liquid? Which one is correct here? Clue gives away which one is a solid. That should help you here. Only one of them starts as a solid. It is A, correct. Yeah, a very solid fixed structure. It starts as a solid and then liquid. It looks similar, but it's more random now and kind of can overlay each other a bit more. So A is the correct one. Well done, everyone. The density of the steel decreases as it melts. How does the spacing of the particles change as the steel melts? So kind of as we saw in the diagram there, what happens to the spacing of the particles? I am doing higher tier questions, Kite. These are also higher tier as well as foundation. So these are both actually. So we are doing them. The space increases. You did this in class. Nice, nice. The spacing increases. Exactly. Yeah, so that's the term I'd use. You can say further apart, but just using terms like increasing and decreasing is always good in science. Yeah. So even if you mentioned the word increase on its own, you actually would have got the mark here. But I would just say the spacing increases. Very good. And then it says, choose from the box below. Melting is an example of what type of change? So state changes are what type of change? Are they chemical, permanent, or physical changes? This is a past paper question. It's not a past paper. It's a variety of past paper questions I've taken based on these topics. I see physical. I see chemical. I see physical. Mostly physical. Correct. It is physical. Okay. Physical because it maintains its properties. Yeah, its property when it goes back to its original change from its original change and the change is reversed, the properties it has stays the same still. Like mass, like we said, mass is still conserved, right? So this is an example of a physical change. Change of state is a physical change. Okay, one thing to remember. Steel is a mixture of iron and a small amount of carbon. Table 1 shows the mass of carbon in 1 kilogram of different types of steel. 4 kilogram piece of steel contains 18 grams of carbon. Determine which type of steel the 4 kilogram piece is made from. You should include a calculation in your answer. So how are we going to do this? So they've shown the mass of carbon per 1 kilogram of steel to determine which type of carbon it is. What type of carbon steel, sorry, it is. If it's 4 kilograms of steel and it contains 18 grams of carbon, what do we do? Someone said times by 4. Someone has said low. Which one is right? A couple of people have said times by 4. And someone has said divided. A couple have now said divided by 4. Yeah, so I've got a mixed set of answers here. The correct answer is, if you think about it, they've told us 4 kilograms of steel has 18 grams. The only way we can compare to this table is because it says the number of grams for 1 kilogram of steel. So we need to look at, if 4 kilograms is 18 grams of carbon, how many kilograms of carbon in 1 kilogram? So we need to divide by 4. Okay, so we do 18 divided by 4, which is 4.5 grams of carbon per kilogram. Yeah, of steel. So there's 4.5 grams of carbon per kilogram of steel. So where does that sit us? 4.5, it's exactly this. It's medium carbon. Okay, so it's medium carbon steel. That's what we would say. So just medium carbon. That is our answer. Okay, that's how we do it. Okay, and the last one here, the 4 kilogram piece of solid steel was heated until it reached its melting point. The additional energy required to melt the steel was 280,000 joules. Calculate the specific latent heat of fusion of the steel. So specific latent heat, we had the equation before. E equals ml. Okay, so the mass is 4 kilograms and the specific latent heat is 280,000. So then that gives us A. There we go. I rushed that and I've made a mistake. If you guys have noticed, I've not done it right. Yeah, so someone else has said 70,000 because they've done it the right way. Well done, everyone. Yeah, so there we go. I'm going a bit crazy. They've asked us for the specific latent heat of fusion. So we want to find L. So we want to rearrange. L equals energy divided by mass. So 280,000 divided by 4, which gives us 70,000 joules per kilogram. So whoever got that, well done. Well spotted. Yeah, took me a little while. I made a mistake there, but I spotted it. Yeah, always important to check. Always double check your calculations. And that is a prime example of that. Yeah, I'd always had to double check it. Nice, guys. When is this exam? It's tomorrow morning, which is exactly why we're here now. Yeah, last minute cramming just before the exam. Okay, so we got through these topic 3 questions. A lot of people have been asking for a 5 marker. So I'm going to skip back to topic 1 to show you what a 5 mark calculation question could look like. Okay, and a 5 mark calculation essentially will involve more than one equation, basically. Yeah, you always see calculations are 2 marks or 3 marks, sometimes 4. Yeah, but when you go above 4, more often than not, it's because it's 2 equations involved. Okay, and I'm going to see that with the example I'm going here. So give me a second. I should get there. There we go. Okay. So it's about springs on a trampoline. Okay, so I'm just focusing on this one to finish off. 5 more minutes. We'll do this one and then we'll go for our last break before we get into the final topic, guys. We're almost there. We're almost there. Okay. When the child is at position A, each trampoline spring is stretched by 0.56 meters. Okay, 0.56, sorry. The elastic potential energy in each spring is 4.9. When the child is at position B, the elastic potential energy of each spring increases to 8.1. Calculate the extension of each spring when the child is at position B. So they're talking about extension and elastic potential energy, right? So we need to go to our formula sheet and think about what equations are relevant to that. Okay, the equations that are relevant to that, elastic potential energy, or E is half times spring constant times extension squared, right? So I'm going to keep that on the side here. E equals half K E squared, where E is extension and K is the spring constant. Yeah, they want us to calculate the extension of each spring. So we need to determine that somehow, one way or another. Okay, so here they've told us in the initial scenario of A, each spring is has a potential energy of 4.9 joules, and they're stretched or extended by 0.5056 meters. So looking at this equation, that means we know the elastic potential energy and we know the extension of each spring. So we can work out K. Okay, so that means we're going to rearrange this. We can rearrange it or we can substitute. I'm going to substitute. Okay, so 4.9 equals a half times K times 0.056 squared. Okay, and now we're going to rearrange. So we want K to be on its own. So we're going to divide everything on that right hand side. So K is on its own, meaning K equals 4.9 divided by a half times 0.056 squared. This is going to give us our spring constant. And that, if someone has that, let me know. Do you know if they have this value? I'm just going to do it in my calculator now. Testing my calculator skills. Let's see. Always good to do that because sometimes people put everything in a calculator at once and get the wrong value. So it's one thing to check. Okay. Always do it step by step. Tima's got it. 3125. Can anyone tell me the unit for the spring constant? Testing you here. What is the unit for spring constant? 3125. More people have got it, which is good. 31.25 isn't quite right. So careful there. Really good, guys, the people that have got that. Newtons per meter. Okay. It's the amount of force you need to stretch an object. So how much force you apply to get it to stretch every meter. So Newtons per meter. Very good. Cool. So we've got that, but that's not what it asked us for, is it? It's a calculate the extension of the spring at position B. Position B is talked about in this next section. So you can see we've got about 2 to 3 marks for this first bit, but we need the extension of it at position B. So at position B, the potential energy of each spring. So you know what? I'm going to split this up. I'll say position A here. We've done this calculation. We're now on position B. We've worked out the spring constant of the trampoline spring. That doesn't change, right? A set material has a specific spring constant. So that's going to stay the same. So I'm going to say K equals 3125 newtons per meter. That's still the same. But now they've told us in position B, the potential energy in each spring, EE, is 8.1 joules. But they want us to find out now the extension. So we don't know what E is. So it's the same 3 letters. So in this case, we're using the same equation, but we're using it differently twice. So like I said, always 2 equations. In this case, it's just the same equation, but using it differently. Okay. Same equation being E equals half KE squared. So let's put in the numbers we have now. 8.1 joules this time. And that is half times the spring constant of 3125 times E squared. Last time in position A, we wanted to take K on its own. So we divided everything else. Here we want E squared on its own. So we divide everything else. E squared equals 8.1 over half times 3125. And a bit sometimes people forget, it's E squared here. We want E. So to get to E, we square root. So what we do on the left, we do on the right. So it's square root of all of that. Now, I see some people have dropped this answer in the chat for some time, and I think they would have been right, but I'm going to follow it through to complete it. If you put that in your calculator and don't forget to square root it, you get a value of 0.072 meters. There we are. That is your answer for 5 marks. Yeah, 5 marker, basically 2 equations. Whenever you see an equation question that is more than 4 marks, more than likely it's going to need you to use 2 equations. Okay, that is a tip there, just to see if you can spot that. Okay, guys. If that doesn't make sense, obviously take a look through this again. How I walk through that. I tried to step by step it with the equation and what equation we need. It's always knowing what equation you need to use. That is what unlocks you a calculation question. Write down, as I always do. I've done it throughout today, and I always do it. It's become force of habit. Underline what information they've given you and identify what that is. Yeah. So if I go through it now, stretching, that's an extension. So I put E. 4.9 is an energy. So that's EE. That's another energy, EE. And there we go. So I know what I have and then what I need to find. This is combined and triple foundation and higher. This is more likely to be a higher question. It can come up in foundation as well, though. There is an equation for that. The equation is in your formula sheet. So that's given to everybody. Yeah, so it can come up for anyone. Okay, brilliant, guys. I've just got a minute over the 8:30, but I got back to the question I promised I would get back to. It would have kicked me if I didn't get back to it. So I'm glad we got there to look at a 5 marker of a calculation. Thank you, guys. Great pushing. Thanks for bearing with me. No problem. You're welcome. I'm glad it could help you. Obviously, look back at this again and skip through and skim through any part of this video again before the exam if you want to look over anything one more time. I know people hate this subject. Some people love it. I actually like it. But it's taken a time to get there. I know initially I didn't so much, but I do like it. So thank you, guys. Take a break too. Appreciate that. I will take this break. 10 minutes. It's 8:31. Our final break. 10 minutes. I'll see you at 8:41. Okay. I'm going to put it in the chat again. 8:41. Come back for 8:41 and we're going to go into topic 4, the radioactivity topic, the final one. Okay. We're going to get through that, try some questions, and we'll call it a day there. We would have gone through the entire topic one, right? Paper one, right before your exam. Hopefully, it gives you great preparation for it. Will this be on for physics paper two and chemistry paper two? Yes, it will be on for all of them. When I go to the break screen, you'll see the dates there. So you guys can take a look at that and you'll see the times for it. Take a look at the link in our bio where you can sign up to those. Okay, so these ones are obviously free. For those ones, paper two, it's a lot more content heavy, and they are just £10 each session. Okay, so if you join for chemistry and physics only, that's £20. Okay, so take a look. We're doing exactly the same thing, covering the key topics that we need to that we think may come up, things that come up frequently, very important parts of bits to remember, just to give you your best preparation for paper two. Magnetism is paper two, exactly. Okay, guys, have a good break. I'll see you at 8:41. I keep saying 9. 8:41, guys. All right. Thank you very much. You can go to the toilet now. Thank you. All right, guys. Hello. Welcome back for the last time for Physics Paper 1 and for Paper 1 Sciences as a whole. We have made it to the last hour, the last section of this cram class. I say an hour. Really, I want to keep it to 50 minutes so you can get out at 9:30, give the rest of the evening back as you start to then wind down before your exam tomorrow. We've gone through 3 of the 4 topics. Don't worry, just give it your best shot, guys. And all we're trying to do is just help you just try and keep in some last minute information. Okay. It's not the be all and end all. That tonight wasn't defining your exams. Just give it your best shot tomorrow. That's all you can do. Okay. And all we're trying to do here is just give you some little bits here and there that hopefully maybe will stay in your mind for tomorrow as well. Yeah. And any bits maybe you didn't catch that you can hopefully remember those for tomorrow. Okay. It has been a long run, Philip. You're right. Been here since September. You've grinded it out and been down to the last 2 weeks. Yeah, so actually incredible. Weeks and weeks of classes, and you've come to the end of it. 2 more weeks to go. Keep pushing, guys. All right, let's do it. So, topic 4. Topic 4 is to do with radioactivity and nuclear radiation and such like. I saw someone mention. Sorry, I saw it in the chat before I dropped off, and someone's just said it. Layla, astrophysics is not for combined, it's a triple only topic, so we're not covering it today. If you want to look at anything on astrophysics, please do take a look at the boot camp session that we did. The video is available on our page. Take a look, and you can see at the end of it, we did astrophysics. So take a look at that if you want. Astrophysics is everything to do with space, basically. It's not a combined topic, so I won't be looking at it today. Okay. So we looked at nuclear equations first of all. So this is one that comes up. So nuclear decay. So when we talk about the different types of decay, the different types of radiation that is emitted, we look at the equations for those. So we'll go into that. The next one, a lot of people had asked for it earlier, half-lives and radioactivity, how it's random in its nature. There's a lot of the time it does come up. Look at this, for foundation and higher, triple and combined, it comes up almost every year. Yeah, triple didn't come up in 2022 and 2024. Every other year it came up. Paper 1 higher, it came up every year bar 2021. So you can see it's a very frequently occurring topic. And then we have contamination. So something I wanted to cover, contamination and irradiation, is one that is important and it does come up fairly frequently, mostly about the definitions of what the differences between the two are. And people do get this mixed up. So it's just something I want to clarify for you all. And that is the main parts of this topic. Okay, so first of all, history of the atom, you're right, it does come up. It's a combined chemistry and physics topic. So I know you guys have done it in chemistry, so I'm not going to go with it again because you've done it already. There may be a question on it in here, but you know it's in both. So I didn't want to go through too much of it. I just want to go through the stuff that comes up frequently in physics as physics and not just both, because I'm sure you guys have covered the model of the atom now. Okay, so the 3 types of radiation, that's where I'm going to start. What are our 3 types of radiation, guys? Can you tell me the 3 types of radiation that is emitted from radioactive substances? This is nuclear radiation, the final topic in AQA Physics, Paper 1. Alpha, beta, and gamma. Excellent. Okay. So, alpha, beta, and gamma. I'm putting the symbols for them. Can anyone tell me what an alpha particle is? What is an alpha particle or alpha radiation? Is it a particle? Is it not? Everyone's got the right answer there. 2 neutrons, someone said. Someone said positive. Someone said helium nuclei, helium nucleus, helium nuclei. Now it's coming in. There we go. Yeah, a helium nuclei. Nuclear fission we are not doing today because it is a triple topic. It's not a combined science topic. It's a triple only topic. Again, in our bootcamp videos, do check that out. It's a helium nucleus. So I'm going to put the mass number and atomic number for helium, which is a mass number of 4 and atomic number of 2. So 2 protons and 2 neutrons. So it has no electrons. It's a nucleus. So it has a positive charge, plus 2. Beta, what is a beta particle? Is it a particle? Is it not? 0, -1, someone jump straight in there. What is it? It's a high-speed electron. That's why we say -1, because usually an atom has a proton as well. It's not an atom, it's just an electron, so it's -1. Just an electron. We say a high-speed electron or fast-moving, exactly. Okay, charge of -1. What is a gamma particle then? I see someone's answer. Good. Okay, no one was thrown off by the fact that I said particle. Very good. It's an electromagnetic wave. It's an EM wave. We see it in the EM spectrum, which is in paper 2. EM wave, an electromagnetic wave, it has no charge, it has no mass because it's not a particle and it has no charge. Okay, so those are the different types. Now the differences between them, we need to know which is the most ionizing and which one is the most penetrating. So which one's the most ionizing out of these guys? Ionization, remember, is the ability to turn an atom into an ion. Alpha is the most ionizing. Excellent. Yeah, so I'm going to say from left to right, increasing ionization. What about penetration? So what it can pass through. Which of these three types is the most penetrating? Gamma. Excellent. Yes, so I'm going to draw an arrow right to left to say increasing penetration. Excellent. People have mentioned what it's stopped by. So alpha is stopped by paper, correct? So I'll put stopped by paper. And also you need to know its range, okay? So its range is a few centimeters in air. What about for beta? Beta isn't lead. Gamma is stopped by thick lead or concrete. Beta, someone said it, aluminium foil, thin aluminium foil. Okay, so stopped by aluminium foil. And it has a range up to 1 meter in air, we'd say. Okay. And then an EM wave, as we've said, is stopped by thick, not just thin, but thick concrete / lead. Yeah, so either, that's the kind of material it's stopped by. And what is its range in air? There we go. Someone said it. It's infinite. Yeah, it has an infinite range in air. Very good. Yeah, and based on those properties, they have different uses. Yeah, different places in which they are more useful. Okay, so that's the different types of radiation. Then we've got, in all of those, they all decay, right? So when they decay, when we talk about radioactivity, what is the sorry, lost my train of thought. When we're talking about decay, we talk about the term activity, the activity of a radioactive sample. Anyone know what activity is? The arrows are correct. The arrows are correct. I'm going from right to left. So from gamma to beta to alpha, the ionization power is increasing. And from alpha to gamma, the penetration power is increasing. The arrows are correct. Okay. It's spontaneous. That's true. Count rate is something else. Becquerels is the measure of activity. It's related to half-life. The rate at which nuclei decay, somewhat closer. Okay, really good that I brought this up. Okay, so it's one that people need to know. Activity, essentially, by definition, is the number of decays per second of a radioactive source. Decays per second of a radioactive source. Okay, so that is what it refers to, and it's measured in becquerels. Yes, you can say it's either measured in decays per second or becquerels. And in symbol form, becquerels is capital B, small q. Okay, so that is what activity is. Okay, so decays per second. Yeah, someone else has said. Excellent. Yeah, so the number of decays can relate to the number of radioactive nuclei. So if you think about a substance, okay, it has a certain number of particles that make it up. Every second, if it's radioactive, some of those particles are going to decay and they'll just disappear because they'll die off. Basically, decay means to die or kill off. Basically, okay. So the number of particles that do die off or decay per second, that is what the activity of a radioactive substance is. Okay, so the activity is the number of decays per second. Okay. Now, the next thing here is to talk about a key thing: half-life. Loads of people have asked about this throughout the session today, and this is very important. There are multiple definitions for half-life. I'm going to give you them all, and you can just pick the one that you prefer the best. Okay. So half-life. Half-life, as the name suggests, is for the life of the radioactive substance to become halved. Okay, and the way you measure that halving can be for multiple things. It could be for the time it takes for its activity to halve, so the rate of decaying to halve. It could be one. Okay, it could be the time it takes for the number of radioactive nuclei to decay by half. So you go from 100 particles to 50. That's the half-life. Yeah, so the time of that to half. It can also be, someone mentioned the term, the count rate. So count rate is when you count the amount of radiation, usually with a Geiger-Müller tube or a GM tube. Maybe you did it in school where you hear the clicks, and every click is a count, and you count that and in a particular time. So let's say I've measured 60 counts in a minute. The half-life will be the time it takes for that to go from 60 counts to 30 counts a minute. All options for half-life. Okay, so I'm going to put those here. So I'm going to put time it taken for the activity of a radioactive substance. To halve, or I should have left a gap here. Sorry, I'll leave a gap. Or time taken for the number of radioactive nuclei to decay by half, or time taken for the count rate of a radioactive substance. Not substance, you know what that is? Substance. To halve. Okay, those three are our options. Okay. On the mark scheme, it does show all of these three. That's what I'm telling you. So pick one of them. Whichever one you can remember the first, stick with that. Okay. I'm telling you, because some people remember one or the other. So I don't want you to tell you one and then you think, oh, is mine wrong? No, it's not. It's one of these. Okay. Any of those can be right. Okay. So that is for the half-life. So I'm going to go into this here. And like we mentioned with the motion of particles, how do we describe the nature of decay, radioactive decay? Here's what we've got. It's like throwing a dice and trying to land a 6. How often do you get it? Do you get it? Some people say there's a 1 in 6 chance. Does that mean on every 6th turn you get a 6? No, it doesn't. It means there's a 1 in 6 chance, but you don't know when you're going to get it. It's random. Exactly, guys. It's a random process. Okay. So decay can happen completely randomly. So even when you have, if you guys, I don't know if you guys have done it in school with the GM Geiger-Müller tube that I mentioned, when you hear that click for the count rate, it's not a consistent, like say if it was 10 counts a minute, it's not, it's like really random. It could be like, and then a break, and then you hear one, and it's a super random. It's almost like, what can I compare it to? Like, I don't know why it came in my head, but like when you heat up popcorn in a microwave and you hear the kernels popping, it can be super random. It's like that. It's kind of like that. Yeah. So, in the way that we say, we just refer to a dice because when you roll the dice, getting a 6 can be very random. Don't know why I'm thinking about popcorn, maybe because I'm hungry, but there you go. Yeah. So, as we were saying about the time it takes for the number of nuclei to decay by half, let me show you this example. So you can see we have started, sorry, it's a bit blurry on here, but I'm going to zoom in and show you. We started with 32 undecayed nuclei in blue and no decayed nuclei. Okay. Then the half-life is the time it takes for the number of undecayed nuclei to half or decay by half. So instead of 32, after a half-life, that would be halved to 16. Yeah, so you can see it becomes 16. Then the next half-life, remember, is for that to half. So it's not to lose 16 nuclei, it's to half the number of nuclei that were there. So now there's 16. The half-life will then be the time it takes for that to half. So to go from 16 to 8. Ignore this number. This is wrong. Yeah, you can see in blue, it goes from 16 to 8. And then one more time from 8 to 4. And that's where that goes. 4 blue particles are left. Okay. So apologies, ignore these numbers. Just go by the blues. Can you see here? We're all blue, 32 blues to start with. Half-life is then it goes down to 16, and then another half-life again halves from 16 to 8, and then one more time from 8 to 4. Yeah, so that is what half-life is. Okay. So that is what we see for the definition of half-life. Okay, so we've talked about nuclear equations, which we're going to see in a second, very, very relevant to the knowing what the three types of radiation are. So we talked about helium nucleus for alpha, a high-speed electron for beta, and then an electromagnetic wave for gamma. Remember that when we get to decay equations. Okay. The next thing I want to talk about, I was saying was in there, is the last bit here: radioactive contamination versus irradiation. Okay, so in terms of the two there, contamination, if you become contaminated with it, it means you've come into direct contact with it. You've touched the radiation directly. Okay, it touches the surface of something. So if a surface becomes contaminated, there is radiation physically on its surface. Physical contact, direct contact. Okay, irradiation is different because it says is exposed to, but doesn't become radioactive. You can see here, irradiation occurs when an person is not become radioactive. Yeah? If you're contaminated, the object becomes radioactive. You come into direct contact with it. Okay, that's the difference. So with irradiation, it's because it becomes exposed to the radiation. You're in and around it, but you don't become. You're just exposed to it. Basically, that's the difference. Exactly. Someone has just said it. Just as I said that. What timing? Yeah, is when you're exposed to radiation. Cool. Okay. I'm going to mention those two definitions just here. If you want to refer to them, feel free. You can write these down. So contamination we're going to say when object is in direct contact with radiation and becomes radioactive. Yeah. The flip side of that, irradiation, not the flip side, but just a slightly different definition. For irradiation is when an object is exposed to radiation, but does not become radioactive. So if you think of the difference, contamination, you touch the radiation directly. Irradiation is the radiation is around you, but you don't become radioactive. That's the difference. Exactly. So contamination, you didn't get it. So contamination is when you come into direct contact with the radioactive substance. So for example, say if there was like back in the day, they talk about radioactivity being in water. Yeah, there was not pure, it had radiation in it. When you drink the water's come into direct contact with your body. You've now become contaminated because you now have radiation on you. You physically touched it. That's contamination. Irradiation is when there's just radiation in your surroundings, but you don't get contacted with it and you don't become radioactive. That's the difference. Okay, so whether you get the radiation physically on you or not, if it's physically on you, you're contaminated. If it's not physically on you, it's irradiation. That's the difference. Okay. I don't know if you're lagging, but hopefully that makes sense now. I've just explained the difference between the two, and I've written the definitions. Yeah, so these definitions here are the difference between the two. Okay. An example of irradiation, like I was saying, is when it's around you, but you don't touch it. That's the example. Okay. So for example, here, you see this. When you have a barrier between yourself and a radioactive substance, you prevent irradiation because it can't be around you even. Yeah. But here on a person, you wear something to cover yourself so that you don't touch it at all. So you avoid touching. It's around you and you don't touch it. When it's around you, you're irradiated. When you touch it, you're contaminated. That's the difference. Okay. Cool. Let's take a look at some questions then, okay, to evaluate the both. Now, so let's get into this. First one. Some people used to think that radioactive substances had health benefits. 100 years ago, a company made a toothpaste containing the radioactive isotopes radium-228 and radium-226. Figure 3 shows the symbols of these radioactive isotopes. How are atoms of radium-228 different from radium-226? So looking at the numbers here, what do you think? Two, three, C. So people have said 2, people have said 3. A lot of people are saying the third answer, radium has 2 more neutrons. You'd be correct. Yes. So because from chemistry and also in physics, when you're talking about an atom, you talk about this top number, which is this mass number. That is protons and neutrons. The bottom number is your atomic number, otherwise known as just your proton number, number of protons. Yeah. So you can see here, they're both radium. They're the same element. They have the same number of protons. The protons don't change. So the top number is protons and neutrons. So for them to be different, it has to mean a different number of neutrons. And 228 has 2 more neutrons. Hence, this number is 2 larger. Okay. Figure 4 shows how the activity of a sample of radium-228 changed over time. Here we go. Someone was asking for it. Here's an example. What is the half-life of radium-228 based on this graph? What do we think? So, 4. It's, remember, one of the definitions, the time it takes for the activity of the substance to halve. So if its activity started at 100, for it to reach 1 half-life, we need to look at where it is at 100. So we go from 100. We draw a dashed line across to the graph. And I'm going to go down from the graph here. So that corresponds to somewhere like 5.7 or 5.8 years. That is the half-life. How can we verify this? Let's see. When would the next half-life take place? That will be from 100 to 50. That's when it halves again, right? That's the next time it halves. So if I go there, I go all the way across, I end up at this one here. That's 11.4. So you can say 5.7 or 5.8 is about right. That is the correct. See, everyone's saying 11. Yeah, it's near to 11, but you need to be accurate here. It's 11.4. I'm just showing you a second half-life to show you the time it took to go from 200 to 100 is the same time it took to go from 100 to 50. And that's the thing about half-life here. My head's in the way. Yeah, you're right. You're right. Sorry. No wonder you guessed 11 only. There we go. And that's where it goes. Okay. So I just showed you the second one, but really to get the mark, you only need to show one half-life. So you go here. And yeah, if I zoom in, it probably is more like 5.7 than 5.8. Yeah. But they'll give you some range there. And even then, if you look at the answer here, even 5.8, 5.7 isn't there. It doesn't matter. You're rounding it. So it's going to be 6 years. Does a long half-life mean it's more stable? Yes, in a way, because then the radiation is being released over a slower period of time. So you're not getting as much of a burst of radiation being released. So in a way, it's kind of more stable. You can say that. Notes will be accessed after the video. That's fine. History of the atom. Someone said, can we go through it? Someone, I'm going to mention it here just because someone's mentioned it now. Who can tell us the mnemonic? I think I saw it at the very start. What is the mnemonic for history of the atom? I'm going to do this in red so you can see it. Yeah, people are getting it. DJRBC, okay? And that is to remember the names of each of the scientists that came up with the discovery, okay? So we start with, and I'm going to write this vertically, John Dalton. Dalton came up with the plum pudding model. Yeah, so that's the first one. So I'm going to put it here. Cram it in as much as I can. I'm going to zoom in, actually, so you can fit it in. So Dalton came up with the plum pudding model, which was a sphere of positive charge with dots of electrons embedded in it. Yeah, so then it looked like a plum pudding. The next one, not J.J. Thomson, but J.J. Thomson. Okay, so J.J. Thomson is the next one. I'll go that way vertically. And J.J. Thomson, what did they do? What did they discover? You can tell me. You can tell me. J.J. Thomson. Proton charge, proton atoms were invisible. Yeah, so yeah, it actually depends how you want to look at this. You can say the important thing here is that how the structure of the atom was formed. So if I go, you know what, instead of me writing it, it's easier to show you on here because my writing isn't going to be very clear. So let's go here. Okay. So Dalton, apologies, that's my bad. Dalton came up with the sphere only. Thomson came up with the plum pudding. Yeah, so that's where we'll put it. So atoms, spherical shapes for particles was what was discovered by Dalton, but he didn't know anything about charge. Correct. He actually didn't know anything about any sort of charges. And then Thomson came up with the plum pudding model, and that's where we got that from. Then Rutherford came up with the alpha scattering experiment. Someone has asked me, do we need to know that? You do need to know it. Yeah, so here we are. What happened in the experiment? It's to do with gold foil. Yes, you have a sheet of gold foil, and then you have alpha particles fired at it. Now, based off of the previous model, you'd expect because particles are just solid spheres, they should just collide all the time. But the experiment didn't find that. It found that there was loads that passed through. Actually, the large majority passed straight through, and then only some were deflected slightly, and some were deflected at very big angles. Only very few. So that told us atoms are mostly empty space. Yeah, and then he found that the mass was very concentrated, and he gave the discovery of the nucleus. Yeah, so the alpha scattering from Rutherford told us atoms are made up of empty space with a concentrated mass called the nucleus. So that's DJR. Then we have B, which is DJRBC. Yep. So Niels Bohr is next, and Bohr came up with the electron shells. Yeah. So around, instead of electrons being embedded in the atom, which J.J. Thomson said, then Rutherford said no. There's a positive charge of nucleus at the center, and then he didn't define where the electrons came from, and that's where Bohr discovered the electrons, and he said that they're in shells or energy levels around the nucleus. And then the last one is James Chadwick, giving the last particle that we added to the nuclear model that we call today the neutron. So we said that the positive charge in the nucleus was from Rutherford, but he didn't state the discovery of neutrons until Chadwick came along. So Chadwick discovered the nucleus, the neutrons in the nucleus, sorry. Okay. Thomson didn't discover the electrons because Thomson just said they were negative charges. They didn't know what they were. He just said negative charges dotted around the he discovered them but not in their position. Yeah, so Bohr discovered their position in shells, but Thomson discovered the electron in the first place. Apologies. Yeah. And protons were discovered by Ernest Rutherford in the nucleus, positive charge, and then Chadwick discovered neutrons. So the order of subatomic particles discovered. Firstly, electrons, because they're called the sphere positively charged. So electrons were discovered first, then protons in the Rutherford experiment, then neutrons by Chadwick. Yeah, the guys in between discovered the positions of things. So Bohr is what we knew about electrons, but just where they were in orbit around the nucleus is what he discovered. Yeah? So electrons, protons, neutrons, EPN, exactly correct. Cool. Okay. Back to this question then. Yeah, so we talked about that. I'll skip this. I'm going to cross this out. It's not as clear on here. Just cramming it in. Probably won't be able to read it after. So there we go. Okay. That wasn't good. Okay. So we did the half-life. Now, this question here. The scientists investigated, I'll zoom in a bit, whether the toothpaste in 4 tubes of the 100-year-old toothpaste is equally radioactive. So they've put this equipment set up here. So they've hung the toothpaste on the stand with a detector on it, and then the sample is underneath. Okay. So then they're using the count rate on this meter to measure the amount of radioactivity. I'm not doing fusion and fission today. It's triple only that topic. Check out our bootcamp videos. Okay, guys. If you want to look at fission and fusion, it's a very brief part of our boot camps. Not brief part, about 10-15 minutes. So you can quickly look at it. So it's time to look at it before your exam. So take a look at that. Okay, so when the equipment was arranged as shown in figure 5, it was not possible to detect alpha particles from the toothpaste. Suggest how the scientists adjusted the equipment to detect alpha particles. So what do you think you need to do? Look at the gap there, 20 centimeters. So what do we need to do to make sure that it's detectable? Reduce or decrease the distance, exactly. This paper is from AQA, but obviously the topics are completely the same for 70% of all boards. So here we're going to say decrease the distance between the detector and toothpaste. Okay. The scientists adjusted the experiment, or the equipment, sorry, and determined the activity of the toothpaste from each tube. And it says what was the range of activities in table 1? So quite an easy one, just an observing one there. What is the range of activities here? You're just looking for the smallest and the largest. B to C, correct. But here it says referring to becquerels, the range of becquerels. So you're taking the values there. Okay, so that's 2940 to 3180. Yes, if you said B to C, you would have got it wrong. So I know, just being picky there, but because they mentioned the becquerel values, you need to give values there. Okay. The range is 240 by calculation, yes, but that's not what they've asked for. They've asked to refer to the values. It's 2940 to 3180, the smallest to the largest. Degree of uncertainty means how your basic measure of confidence in your results. If you go back, we looked at uncertainty in results earlier when we had a range. We did half the range for the uncertainty of the results. Okay, because it's about how sure you are the results are correct or accurate. What if you did it the other way around? It can be in either order. That's fine. Either way is fine, as long as you pick the smallest and the largest. This is for combined, correct? Okay. People have answered this. Sorry, I've missed it. People said B, D, 1/4. A mixture of answers here. What was the independent variable in this experiment? So, majority of people got it right. It is D. It's the tube of toothpaste used. Okay, because that's what we're controlling, right? The mass we're fixing is constant. We're not varying it. The temperature of it we're fixing. It's not changing, and the activity is what we're measuring. It's the dependent variable. So the correct answer is the tube of toothpaste used. What was the dependent variable? So I mentioned it in the I just mentioned it. I should have waited till I saw it in this one. What is the dependent variable? This is for foundation and for higher tier. Duofalac. Sorry if I said your name wrong. It's for foundation and higher tier. A. Well done, guys. I did say it. The activity is what we're measuring. What you measure is the dependent variable. So it's activity. When the toothpaste was new, it caused a risk to health because of the nuclear radiation emitted. What happened to the risk to health from the toothpaste after 100 years? What would we say there? What would happen to the risk over time? Because if you think about it, more of it is emitted, less of it is left over. Correct, Alfie. The risk decreases exactly due to decay, Sophie. Exactly, everyone. Well done. Yeah, so I'd say there is less risk. What property makes nuclear radiation hazardous? Think about for us as humans, as people, what makes it more hazardous for us? Someone said A and B. Most people have said A. A is correct. Yeah, it's ionizing. Penetrating, it doesn't matter. If it passes through, it's okay. It's what it does to your body that's more harm, and that's ionizing. The ionizes cells in your body. It can cause them to mutate. It can cause cancer. That is the risk. Okay, so it's ionizing that's the hazard. Well done, everyone. Some people used to think that radioactive substances had health benefits. It's funny, I was talking about the water example, wasn't I? Back in the day, water was radioactive. There we go. It's the walls of the revogator, this revogator equipment they used to use, that was radioactive. So it says, some people used to think that radioactive substances had health benefits. In the 1920s, a water container called a revogator was sold. The walls of a revogator contain radioactive isotopes. Figure 6 shows a revogator. The revogator was filled with water and left overnight. People then drank the water from the revogator. The water was irradiated and contaminated by radioactive isotopes in the wall of the revogator. Explain how irradiating and contaminating the water affect the hazard caused by the water. Okay, so here we're looking at, someone was asking, what is irradiation, what is contamination, and how did they harm you? This question tackles exactly that. Okay, so if the water was irradiated, what is the risk? And if it was contaminated, what is the risk? Okay, so If it's irradiating, the radiation reaches the water. What does that do to the hazard? What would that do to the water? Think about water back in the day. Water that they'd keep. They used to keep it and then drink it overnight after leaving it in the revogator. Contamination is worse. Cool. Bear that in mind. That is correct. So whoever said that, that's cool. We're going to do contaminating second. But what about irradiating? Water is infected. That's what I want you to think about. Back in the days, and even any water you take from somewhere that isn't filtered or from a tap, it's not pure, is it? It's infected essentially. There's bacteria, there's pathogens in it. So when there's radiation in the water, there we go. Someone has said it. Sugandhi has said it. It kills the bacteria. Yeah, it kills the pathogens. When you're irradiating, the radiation around the water kills the pathogens in the water, and therefore, if there's less pathogens in it, is the water healthy or not? You're supposed to think back in the day. We aren't that old. Yes, you're meant to think about the hazard of water, right? It says people used to drink radioactive substances and had health benefits. So they're talking about water container and cleaning water. That's what you need to think about. You don't need to think about back in the day. Irradiating, Fabio, I mentioned earlier, is when you're exposed to the radiation. Okay, so the water is exposed to the radiation. The radiation is in and around the water, but the water doesn't become radioactive. Yeah, that's why irradiating is helpful in this case, because the water doesn't become radioactive, but it kills the bacteria within the water. Okay, so we're going to say here, water is exposed to the radiation. And this kills the pathogens in the water, or say this kills bacteria in the water. So therefore, this is safer to drink, isn't it? Because there's no bacteria. So therefore, the risk is reduced. So therefore, 1 mark for what it's doing when it's irradiating, 1 mark for how it affects the risk. Because radioactivity can kill bacteria. That's what it does. Yeah, so alpha, beta, gamma, that can kill bacteria. Yeah, just like we said, it can ionize cells in the body. It can ionize the bacteria and kill it. Okay. And then for contamination, that's when we drink it. Yeah, so when we drink it, because if the water is contaminated, that means the water is radioactive. Then we drink the water, it makes the radiation enter us. That's the risk, and that's going to increase it. It's going to ionize in our bodies. It increases the hazard. Yeah, so not the risk, the hazard. I realized it's asking for the hazard, so therefore the hazard is reduced here because the water doesn't become radioactive. Yeah, so I'll say water is not radioactive. But for contaminating, water comes into contact with the radiation and becomes radioactive. This increases the risk, increases the hazard, sorry. Because now that radioactivity is going to enter your body when you drink it. That's the difference. Okay. I haven't done nuclear equations yet. We're just about to come up with a question on it. But yes, hopefully this makes sense, everybody. Irradiating means it is exposed to radiation, so it can kill the bacteria in there, but the water doesn't become radioactive. Therefore, it's a reduced hazard. Whereas contaminating means the radioactivity or the radiation comes into contact with the water becomes radioactive. You drink radioactive water, that becomes in contact with your body. Now it's inside of you, and that is a risk. It's a high hazard. Okay. Hazard is the danger it causes. Risk is like the probability of it. Yeah, that's the difference. So hazard is like the what the concern is. So what could it do to you? Risk is like the probability of it happening. That's the difference. Yes, I did miss the word contact. Good for spotting that. Good. Comes into contact. Correct. Sorry about that. Well spotted. Okay. Here we go. Someone literally just asked, have we done nuclear equations? Here is a question on it. Okay. A scientist tested some water that had been left in a revogator. The water contained radon-222 and vanadium 52. Vanadium 52 decays by emitting beta particles. What is the correct nuclear equation for this process? So if you're emitting in a nuclear equation, the radiation should be a product. Okay, it shouldn't be a reactant, it should be a product. In every equation, just like in chemistry, you never see a minus in an equation. Yeah, so these two should automatically be ruled out. I'm going to keep those in pen. You never have a minus in a reaction, right? It's the same for nuclear equations. So which of these two is going to be correct? We have vanadium, which is the same on the left. But what happens on the right? We have plus a beta particle because that's been emitted. So we just need to look at the maths of the mass number and the atomic number. So if we look at the top, the mass number is 52. 52 and 0 should equal 52. So that's right. The bottom, however, 23 to then 22 and minus 1. 22 plus minus 1 is 21. That doesn't work. It needs to balance on both sides. So it needs to be 23 to 24 plus minus 1. All of you got it. It's D. It's D. Revigator is just a device they're referring to that was used to think that they thought would purify water back then. Yeah, it's just an old school device. Obviously, we never use it now. We have filters and things like that to purify water. Okay, table 2 shows the half-lives of radon and vanadium 52. The scientists measured the radiation emitted by a sample of radon 222 and the radiation emitted by a sample of vanadium 52. The scientists repeated the measurements 7.4 minutes later. Explain how the activity of the radon 222 and the vanadium 52 had changed after 7.4 minutes. So for radon 222, the half-life is 3.8 days. So in 7.4 minutes, do we think, would that have changed a lot or not? Forgive the rhyme. Would it have changed a lot or not? If its half-life is 3.8 days, would it have released a lot of radioactivity in 7.4 minutes? Not exactly. Yeah, it wouldn't have changed a lot because the not a lot would have changed. The activity would be relatively similar, right? Would be very similar. So I'd say activity is almost the same because 7.4 minutes is just a fraction of 3.8 days. It's barely any time when you think of 3.8 days. Yeah? So you could say the time is much less than the half-life. So I'll say activity is almost the same for 1 mark as the time of 7.4 minutes is significantly less than the half-life. Than the half-life, and you can say of 3.8 days if you want, just to show that you know what you're referring to. Okay, so that's how it works for radon. How about for vanadium 52? The half-life was 3.7 minutes. So what would have happened to the activity of vanadium after 7.4 minutes? Yeah, Alfie, nice. Very, very good answer. Yeah, exactly that. Yeah. We know 3.7 is 2 half-lives. 7.4 divided by 3.7 is 2. So it would have had 2 half-lives that have passed. Half times a half, then it becomes a quarter of what it was. Yeah. So what I would say is it decreases by a factor of 4, or it becomes a quarter of what it was, as some of you guys have said. Okay. So which bit don't you understand, Fakimi? I need you to be a bit more specific. Here, 7.4 minutes, if it have passed. If a half-life is 3.7 minutes, 7.4 over 3.7, that's 2. So 2 half-lives would have passed. And in a half-life, its radioactivity would have halved, right? So let's say the activity was 100 becquerels to start. After 1 half-life, it would have halved to 50, right? And then we said there's 2 half-lives. So the second half-lives, halve again to 25. So if we look after 2 half-lives, it's gone from 100 to 25, divided by 4. So decreased by a factor of 4, or a quarter of what it was. 100 becquerels is my reference number, Sarah. I've just given you a random number. I could have said 1,000. I could have said 20 million. Yeah, but I'm just showing you by numbers. I'm showing you after 2 half-lives, it's a quarter of what it was. I just want to explain where the quarter has come from. So I would say for 2 marks here, activity will decrease by a factor of 4 for 1 mark. And the reasoning, as 2 half-lives have passed in 7.4 minutes. That's how I get the 2 marks there. Yeah. Okay. Excellent. So that's 4 marks there. Okay. So for each one, what happens to the activity and the reason for why. So radon, really long half-life. So the time was very insignificant. So the activity barely changed. 2 marks. Vanadium, 2 half-lives have passed. So it decreased by a factor of 4 in its activity. 2 marks. Okay. Scientists monitored the effects of drinking water from a revogator. Their methods and results were checked by other scientists. What is the name of the process given for other scientists checking work before it's published or released? Valencia straight in there before anyone else even said it. There we go. A few others are saying it. Peer review. Correct. Okay. Peer review is what we call it. Excellent. Brilliant. Okay. It's 27 past, 3 minutes left. I'm going to say we leave it there for today. We will send you the mark schemes for this. I'm just going to mention one part of a question. Where was it? Let's see. There was one I wanted to say. Not that one. No, okay, it was the first part. Just the first part, and then I'll mention someone else for some tips if you want to. So just quickly, a smoke detector contains a source of alpha in a plastic case. A source of beta would be more hazardous than alpha. Why would that be the case? So why would beta be more hazardous than alpha in the case in a smoke detector? Why would it be more hazardous? Because in a smoke detector, yes, people have said it, it's not ionizing. It's the one that other people said. It's about its penetrating power. It travels further. So the point of a smoke detector is when the smoke appears, it should stop the alpha from passing through. The alarm goes off. But if it's beta, whether there's smoke or not, the beta will keep passing through. You won't realize that there's smoke. The alarm won't go off. That's dangerous. You want the alarm to go off. Okay. So we'd say for 2 marks, beta is more penetrating than alpha. Yeah, so you're stating the property. That's the difference. And then why is that an issue? Because then that's going to allow the radiation to pass through. Yeah, so it can pass through or pass through the smoke. Allowing beta to pass through smoke and also irradiate the people around it, right? If you're living in your house, you'll be irradiated by this. So that's the risk. Okay. Cool, guys. I'm going to leave it there in terms of content. Well done, guys. We got through it. 4 hours later, here we are. And Electra, shout out to Philip. Yes, shout out to Philip, a guy that's been here from the beginning. He's been here with us since September. He's joined us for every session and been a massive part of our journey this year. And he's vouched for us along the way. So thank you very much. Thank you to all of you that stayed here till the end. Thank you for all of you that joined. Massive good luck to you all. It's the final night before. Just try and get a good rest, guys. Don't stay up too late if you can help it. If you feel behind, then do it. And you've got the content to help you. But otherwise, do a little bit tonight. Get a good rest. Do a little bit in the morning on the way to the exam. And just read over some stuff. Go over some key topics in your mind. Good luck to all of you. The mark schemes are going to be sent to you for these. So the questions I didn't cover, and even for the ones we did, you can see what I mentioned about what they show in the mark schemes. So do take a look at that if you like. But other than that, good luck. Thank you so much for taking part. Hopefully it goes really well tomorrow. Hopefully some of this does come up. I'm sure some of it will, not none of it. So definitely some of it will come up. And I hope you get the questions that you want. And good luck, guys. And then I will see you guys. Like we said, we've got our cram classes for the other sciences coming up for paper 2s. So after these ones are done, we'll see you in next Sunday for biology paper 2, next Thursday for chemistry paper 2, and then Sunday the 14th, the last one with me on Sunday the 14th of June. So you sign up, check the link in our bio. It's £10 per each of those paper twos. So just take a look. You can sign up with the link in our bio on TikTok, and it will take you straight to the access for our cram classes. So take a look there. Very easy to sign up. And then again, near the time, you get a link to the workbook like this, but for paper two. So exactly the same way, we'll be looking at key topics in those as well. So biology next Sunday, chemistry the following Thursday, and physics on Sunday the 14th. So look forward to seeing you there. Otherwise, good luck. Have an amazing evening. Try and get some rest in. And we'll see you next time with Neen for biology paper two, guys, for those of you that have signed up. Thank you very much. Take care, guys. If you're triple, you do need to know about insulation practical if you're triple science. So take a look at that in our bootcamp videos. Thank you, guys. Glad to hear that it was helpful and that you're thankful for it. Really appreciate that. Thank you very much, guys. The bootcamp videos are on YouTube. The paper one bootcamp videos, you'll find them on our YouTube. You'll also find the entire physics paper one video Nina's released. That's also on YouTube. So check that out as well. Thank you very much. Thanks, Anne. You don't need to send an email for the mark scheme. We'll send it to you. If you've signed up, we have your email and we'll send you the mark scheme. So don't worry about that. If you buy FRL Pro, you do get the cram classes done. So you can do that as well. Absolutely. Obviously, it's less than paying for all three sciences. So you can do that. All right. Loads of people are asking for the last 6 marker. If you want to hang on, I quickly can look at it for you guys. Seeing as you guys have asked, I will go through it. So, guys, this is a good one. This is just a revision of literal factual recall, guys. Okay, so it says explain the different properties of alpha, beta, and gamma. Okay, so you're just comparing what we spoke about, which is the most ionizing, which is the most penetrating, what are their ranges in air, and what are they? What physically are they? Okay, so briefly, just to explain, we'll start with alpha. What is it? We said it earlier, a positively charged helium nucleus. It has a low penetration power. Yeah. And you'd mention what it's stopped by. Stopped by paper, thin paper. And then you can say its range is a few centimeters in air. And then you do the same, but you do it for beta and you do it for gamma. So for beta, this is a high-speed electron, we said. And then we know it's moderately penetrating because it's in the middle, right? It's not as penetrating as gamma, but not more penetrating than alpha. And then we say stopped by aluminium foil, we said. And we said the range is up to 1 meter in air. Range is, up to 1 meter in air. And then for gamma, we said it's not a particle, it's an EM wave. Highly penetrating, and is stopped by thick concrete or lead. And its range is infinite in air. Yeah. And the last thing I didn't mention, I said it, but I didn't write it. Most ionizing for alpha, moderately ionizing for beta, and the least ionizing for gamma. Yeah, that's what we literally. I've just factual recalled the different properties, and that's all they want you to do. So for 6 marks, this is actually quite a good question because it's just talking about each type and giving a few properties of each, and just recalling the facts from it. I would say you mentioned that it's a high-speed electron. Yeah, I would say it's better to mention that's what it is. You can say electron, but I'd say just to be safe, just say high speed. Just say it as a high-speed electron. You're covered then. 2 more words, right? Cool. All right, guys. Covered that. Thank you, everyone, for taking part. I'm going to call it there, and you guys should get a bit of rest as well. You pay for boot camp, but it's over. You have the recordings for the boot camp, no problem for that. So you have access to it even now for the paper 2 boot camps. You have access to them, so that's notes for you to keep and refer to the videos and the boot camp revision guides that we gave you as well. You can use bullet points. Exactly, you can use bullet points for answers as long as you write basically somewhat of a sentence, and you wrote it as bullet points. No problem with that. Okay, guys, I'm going to head off. If you have any questions for us, send them to help@flashrevisionlab.com. You can take a screenshot if you want. Obviously, it's on the. You can check the recording back, obviously, as well. But there you go. You can take a screenshot of it there. Pause anytime you want. But thank you very much, guys. Have a good evening and good luck for tomorrow. Okay, all the best. Just give it your best shot, and just what happens will happen. Okay, thank you, guys. Take care. I'm not doing chemistry and biology. Neen is doing chemistry and biology, and I will be doing physics paper 2. Okay, so thank you, guys. Thanks for your kind words. I'm glad that you found it useful, and all the best. Take care.